Let's take a journey. A journey not through space, but through the very fabric of time, back to an era when our planet was a completely different world. Imagine a time when the Earth itself seemed to be taking its first deep breaths, pulling itself together. This is not a story about human civilizations or the cities they built. It is a saga of gigantic land masses, of continents that for centuries, millennia, millions of years inexorably crawled toward each other. Drawn by forces hidden in the planet's scorching depths, forces so colossal and unhurried that the entire history of humanity would have flashed by in a single, brief flash. This is a story about the very ground beneath our feet. Every rock, every mountain range we gaze upon today was once just a fragment of a grand mosaic, each piece fitting perfectly together. We will be transported to the very moment when this great puzzle was finally assembled, when all the disparate continents merged into one. We are entering the era of Pangea. The history of this supercontinent began long before its name was even mentioned. In those distant times, our world looked unrecognizable. The planet resembled a seething mosaic of volcanic islands, underwater ridges, and endless shallow seas. What geologists call the Earth's crust was already in constant motion, caught up in powerful flows of molten magma deep in the Earth's mantle. To understand this power, imagine the planet's core as a gigantic cauldron of boiling lava, seething molten rock. Red-hot flows of the mantle slowly rise to the surface, cool, and then plunge back into the depths, dragging the solid slabs of the Earth's crust along with them. This titanic waltz, stretching over hundreds of millions of years, is the engine that causes the continents to drift, collide, and separate. This movement seems excruciatingly slow to us, almost imperceptible. But on the scale of geological time, it can change the planet's appearance beyond recognition. When we speak of the birth of Pangea, we are not talking about a single event, but a long process of reunification stretching over millions of years. In the past, continents had already merged to form other supercontinents. Scientists have given them names that echo ancient myths: Rodinia, Nuna. But Pangea was the last such giant, the last unified world before the planet took on its modern form. Its formation occurred between the late Carboniferous and early Permian periods, about 300 million years ago. Imagine this scene. To the north, a huge landmass drifts, Laurasia. To the south, the equally gigantic Gondwana. And now, centimeter by centimeter, they begin their slow journey toward each other. The oceans that separated them for millions of years gradually compress and disappear. And at the points of their collision, where the edges of the continental plates collide, the Earth's crust rises, forming colossal mountain ranges. These were young, growing mountains as tall as today's Himalayas. And so, at the culmination of this great geological ballet, Pangea is born. Not just a continent, but a supercontinent, a gigantic landmass stretching from the ice cap of one pole to the other. Try to imagine its scale. If we found ourselves in the very heart of this land, we could walk for weeks, months, and still not see the ocean shore. In all directions, to the very horizon, there would be nothing but dry land. Pangea's interior was so far from the coast that the moist ocean winds simply couldn't reach it. This meant the birth of a harsh climate, scorching heat during the day, freezing cold at night, months-long droughts, and endless dead deserts stretching for thousands of kilometers. Even the air itself was different here. The oxygen content in the atmosphere fluctuated constantly, and winds swept across the vast plains unimpeded. The planet's climate as a whole was unstable. Periods of heat and drought alternated with ice ages, but life never ceased for a moment. And the creatures that inhabited this world were truly astonishing. The planet was undergoing one of the most dramatic transitions in its history. The era preceding Pangea, the Carboniferous period, was a world of endless swamps and damp, gloomy forests. Imagine giant ferns as tall as trees, colossal horsetails, and air so rich in oxygen that monstrous insects could thrive in it. But with the unification of Pangea, everything changed. The climate became increasingly dry, and the lush, swampy jungles began to retreat. They were replaced by more resilient plants, the first conifers, seed ferns, and other species capable of surviving in arid conditions. This change in scenery triggered a new wave of evolution. Insects were forced to adapt. A huge diversity of reptiles emerged, including the first ancestors of mammals, our distant ancestors. Their warm-bloodedness became the key to survival in a world with such dramatic temperature fluctuations. Pangea itself was a patchwork of different worlds. Along the coasts and in the river valleys, forests still remained, providing shelter for amphibians, reptiles, and early synapsids. Deeper inland, sun-baked plains stretched, where life was a struggle for survival. And closer to the poles, the climate remained cold and unpredictable. Ice caps advanced and retreated, obeying the slow cycles of the planet's rotation. In every corner of this world, life pulsed to its own rhythm, reflecting the tectonic drama playing out deep within the Earth. The oceans lapping the shores of Pangea were no less majestic. Panthalassa, a single global ocean, encompassed almost the entire planet, and to the east, wedged between the converging continents, lay the Tethys Sea. The waters of these ancient seas teemed with life. Ammonites swam here in their spiraling shells. The last trilobites clung to existence. And in the depths, primitive sharks and armored fish hunted. Coral reefs rose in the shallows, but they were built by completely different corals than the ones we know today. Ancient Rugosa and Tabulata created their own underwater cities long before the emergence of modern species. But how did we learn about this lost world? The story of Pangea is the greatest mystery left to us by the planet itself. Clues are scattered across the globe. Remains of the same ancient animal are found, for example, in South America and Africa. How could it have crossed the Atlantic Ocean? Rocks on the east coast of North America are a perfect match in composition to rocks in Scandinavia. And if you look at a map, the outlines of the continents look as if they could fit together like pieces of a giant puzzle. And at the beginning of the 20th century, someone dared to piece together these clues. The German scientist Alfred Wegener put forward a truly revolutionary idea. The continents aren't stationary, they're moving. At the time, the scientific community greeted his theory with ridicule. The very idea that entire continents could drift across the planet's surface seemed absurd, but decades later, the evidence became irrefutable. The study of ancient rock magnetism, exploration of the ocean floor, and finally, the discovery of tectonic plates, all of this brilliantly confirmed Wegener's correctness. Today, his theory underlies all of modern geology, and when we speak of Pangea, we stand on the foundation laid by this courageous scientist. The formation of this supercontinent was a process spanning tens of millions of years. The northern continent, Laurasia, arose from the merger of what would become North America and Eurasia. The southern giant, Gondwana, united the lands that are today South America, Africa, Antarctica, India, and Australia. When these two titans collided, Pangea was born. Along the line of their collision, the Earth's crust crumpled into folds, like a tablecloth on a table. This is how the Great Mountain Ranges emerged, where today lies the eastern United States, northern Europe, and parts of Africa. Mountains comparable to the Himalayas arose. Today's Appalachians and the Ural Mountains are merely the time-worn remnants of those majestic peaks, witnesses to the monstrous force of the collision of worlds. It's difficult to even comprehend that the continents we perceive as immutable were once a single land. Welcome to a planet where the laws we know don't apply, and science takes centuries to comprehend what it has seen. Now we'll travel back in time again, to that distant era when the world itself was just coming together. This story isn't about people or the machines they created, it's about continents that, driven by invisible forces, slowly drifted toward one another. Their movement was so leisurely that an entire human life would seem like a fleeting moment. This is a story about the Earth itself, about the rocks and soils on which we stand. Every city, every mountain we know today was once just one piece of a single gigantic puzzle, all the pieces of which fit perfectly. We will be transported to a time when this puzzle was finally assembled, when all the disparate parts of the land came together, becoming one. This is the era of Pangea. Just imagine for a moment that we stand on a tiny fragment of that ancient world that existed long before the events we're about to discuss. The mere thought of sitting on the remnants of a supercontinent still slowly moving through the endless stream of time is breathtaking. So, let go of the fuss. We will not rush, because the whole world around us is slowing down. The story of Pangea began long before it was given a name. In those days, continents did not yet exist as we see them on maps. Let us travel to a world that existed long before us. The world of a single continent, Pangea. Contrary to expectations, it was not a silent desert. No, this era was filled with movement, slow but inexorable, meaningful and full of purpose. Creatures of the most unimaginable shapes and sizes inhabited every corner of this supercontinent. From coastal areas caressed by the warm waves of an ancient ocean to scorching deserts shimmering in the very heart of the land. It was a world that tested the endurance of every living organism, a world that challenged survival like no era before it. Existence on Pangea meant a perpetual struggle with scorching heat and debilitating drought, adapting to vast distances and finding one's place in an ecosystem that could be a generous provider one moment and a merciless executioner the next. Seasons shifted with alarming speed, and all life spread across the planet was forged in the crucible of extreme climate swings. Along the coastlines, where the moist breath of the ocean still reached, dense forests stretched. But don't imagine the lush, impenetrable jungles of earlier eras. No, these were rather harsh landscapes dominated by tall conifers, giant tree ferns, and the first seed plants. Their leaves were tough, covered in a waxy coating, a natural armor that allowed them to resist the evaporation of precious moisture under the merciless sun. These forests stretched along river valleys and vast deltas, places where water and fertile silt created ideal conditions for the emergence of complex food chains. The air here was thick and sticky with moisture, filled with the incessant buzz of insects and the subtle rustling of small reptiles scurrying among the dense tree roots. Amphibians lived along the edges of ponds and streams, their fate inextricably linked to water. The air was thick with the scent of resin and damp earth, mingled with the subtle scent of salt carried by the wind from the ocean. In those distant times, these forests were cool and pristinely quiet, broken only by the sounds of nature. And who inhabited these ancient forests? The creatures that inhabited them were diverse and truly amazing. The dominant vertebrates of that time were not dinosaurs at all. Their era had not yet arrived. Their distant relatives, the synapsids, ruled here, as well as reptiles that would only become the ancestors of the great lizards millions of years later. Among the synapsids were species that would eventually give rise to all mammals, including us, although at that time they more closely resembled strange reptiles. Some of them, like the famous Dimetrodon, sported a huge bony sail on their backs, which most likely served as a natural radiator for regulating body temperature. Others, smaller and more agile, combed the forest floor in search of insects and other small creatures. These creatures were already warm-blooded, or were on their way to becoming so. Their metabolism was much more active than that of cold-blooded reptiles, which gave them a huge advantage. They occupied the very ecological niches that mammals would later take over. Their existence was merely a prelude to the great events that would shake the planet. In the shallow lakes and swampy marshes, among dense thickets of reeds and ancient grasses, a drama of its own unfolded. Amazing creatures inhabited these lands, marking an entire era in the evolution of life. The coastal marshes remained the realm of diverse amphibians. These creatures were direct descendants of the planet's most ancient inhabitants, perfectly adapted to a dual life, in the water and on land. Some of them reached impressive sizes, possessing broad, flat heads and bodies built for ambush hunting. Like living traps, they lingered beneath the murky surface of the water, waiting for unwary prey to snatch with a lightning-fast lunge. Other amphibians were smaller and more agile, nimbly gliding between the stems of aquatic plants. Their delicate skin required constant moisture, so their entire lives were spent on the border between two worlds, aquatic and terrestrial. The rainy season was a time of rebirth and reproduction for them, when the flooded lakes created countless temporary pools, ideal for spawning. But when the heat returned and the water evaporated, many of these temporary shelters turned into death traps. Thousands perished, but the most resilient always found refuge in deeper lakes, waiting for the next rain and continuing the eternal cycle of life. The further we travel into Pangea, the more hostile the world becomes. Here, in the heart of the supercontinent, living conditions were far more severe. The climate was unforgiving, the air dry and hot, the soil rocky and barren, and rain incredibly rare. Only the most resilient and adaptable species could survive in this hell. Vegetation here was sparse and stunted, only tough, thorny bushes and rare, stunted conifers clung desperately to the rocky ground. Their roots, like tentacles, reached deep underground in search of even a drop of water, and their tiny leaves were designed to conserve every molecule of precious moisture. The animals that inhabited these parched lands were no different. Reptiles, clad in thick, scaly armor, moved slowly and deliberately, conserving every joule of energy under the scorching sun. Some hid from the midday heat in burrows and crevices, emerging to hunt only at dawn or in the cool twilight. A world of insects and small arthropods teemed among the rocks, feeding on dry plant debris or preying on one another. The desert ecosystem was extremely simple, yet surprisingly resilient. Each species played an indispensable role in this fragile balance on the brink of survival. But even in this realm of rock and sand, rivers flowed. Their courses were constantly shifting, subject to the whims of geology, but they were true arteries of life. These rivers served as a lifeline, allowing narrow ribbons of green to cut through the red desert dust. On their banks, vegetation was much richer, and life flourished in abundance. Fossil finds made in these places tell us a remarkable story. We see the tracks of animals that came here to drink. Claw and tail imprints, pressed into the damp mud millions of years ago, fossilized over time and are preserved to this day. Entire herds of reptiles roamed these waterways, grazing the succulent coastal vegetation and laying eggs in the soft, moist soil. And predators followed relentlessly in their tracks. Their paths wound along the same riverbeds, for where there is prey, there will be a hunter. Every drought transformed the rivers into a network of cracked clay crusts, but every flood, however rare, brought new life and fertility. Life here was cyclical, patient, and perfectly attuned to the harsh rhythm of scarcity and abundance. Let's look up at the sky. Birds weren't there yet, but it was far from empty. Insects reigned supreme. Giant dragonflies, with wingspans comparable to modern falcons, soared above the surface of the water. Their flight was confident and precise. Beetles, cockroaches, and ancient relatives of modern wasps and crickets performed vital functions. They pollinated plants and served as cleaners, participating in the process of decomposition of organic matter. The incessant buzz of millions of wings would have been a constant soundtrack to the Permian period. Many of these insects were smaller than their giant carboniferous ancestors, perhaps due to declining oxygen levels in the atmosphere, but their diversity, on the contrary, increased exponentially. They fed on everything: plants, pollen, carrion, and each other, forming a complex energy network that linked together all ecosystems, from humid coastlines to parched deserts. Now let's dive into the open sea, into the waters of the gigantic Pangea Ocean, where the history of life was no less fascinating. This global ocean was home to a stunning diversity of marine flora and fauna. Many species were already beginning to evolve into the forms that would dominate the planet in subsequent eras. Coral reefs flourished in the warm shallows, creating underwater cities teeming with life. And in the dark depths of the ocean lay secrets and mysteries that we have yet to uncover. Ammonites and nautiloids drifted in the open waters. Their perfectly coiled shells were true masterpieces of natural engineering, allowing them to control buoyancy. Sea lilies, or crinoids resembling strange feathered flowers, rose from the seafloor, filtering nutrients from passing currents, and sharks hunted on the continental shelves. Some are swift and sleek like torpedoes, others are wide and flat, adapted to life at the very bottom. The deeper we dive, the more mysterious life becomes. The vast expanses of Pangea created low oxygen zones where only a few organisms could survive. These stagnant waters were veritable storehouses of organic matter, which slowly sank to the bottom and accumulated there over centuries. And above them, in sunlit layers, floated plankton, forming the basis of the entire ocean food chain. The ocean was as dynamic and turbulent as the land. Its inhabitants were subject to the same global cycles of warming and cooling as terrestrial species. But life was especially vibrant at the boundary between the two worlds, where land met sea. Coastal zones, islands, river deltas, and lagoons were transitional areas where marine and terrestrial species coexisted. Plants anchored the soil with their roots, stabilizing the shoreline and providing food for countless insects and herbivores. Fish spawned in the brackish waters of estuaries, and amphibians hunted in shallow waters. Fossils found in these regions bear witness to this remarkable fusion of two worlds. Shells and scales, leaves and paw prints, preserved in a single layer of rock, are irrefutable evidence that air, water, and rock at the edges of Pangea were in constant dynamic equilibrium. Inland, the diversity of life was directly dependent on geography. Giant mountain ranges, formed by the collision of continents that formed Pangea, served as both barriers and corridors for migration. On their ocean-facing slopes, rainfall was much more frequent, fostering forest growth and streams, supporting a rich diversity of species. Deserts stretched in the rain shadow on the other side of the ranges. Elevation changes created unique microclimates, small islands of stability in this unpredictable and harsh world. In such refuges, isolated from the rest of the world, species could evolve along their own, entirely unique paths. Let's fast forward to a time when life on Earth was a veritable field for evolutionary experiments. Every living creature, every population, adapted to its unique environment. Some of these evolutionary lines eventually reached a dead end and disappeared, disappearing into the geological record. Others, more fortunate, survived, and their descendants carried the imprint of this ancient world through the millions of years that followed. The entire history of life during the Permian was permeated by a spirit of ruthless competition and constant innovation. Reptiles experienced their first flourishing, evolving rapidly and producing an incredible diversity of forms. It was at this moment that those groups of animals, destined to become dominant forces in future ecosystems, began to emerge onto the stage of history. We see the emergence of the first, still primitive ancestors of turtles, lizards, and formidable crocodiles. Among synapsids, mammal-like reptiles, some species took the path of complexity. They acquired specialized teeth and more powerful jaws, opening them up to a new, wider range of food. These seemingly insignificant advantages accumulated over generations, becoming the engine of monumental evolutionary changes. Predators became ever faster and more deadly, and their prey became increasingly cautious and elusive. Each new adaptation provoked a counter-reaction, setting off an endless arms race that kept life in a state of perpetual motion and development. But not all the action took place on the surface. Let's take a look underground, where a whole world of creatures hid, literally shaping the planet. countless hordes of small reptiles, amphibians, and invertebrates worked tirelessly, digging complex tunnels in the soft ground. They created entire underground cities that, like lungs, aerated the soil and mixed organic matter. These burrows weren't just homes, they served as a reliable refuge from the scorching heat and eternally hungry predators, providing temporary shelter in this harsh world. Fossilized traces of this underground life offer scientists a unique glimpse into the lives of creatures that left not a single bone behind. These ancient tunnels, often preserved in exquisite detail, reveal intricate labyrinths and entire chambers where prehistoric animals rested or hid their food supplies. They provide irrefutable evidence that life in that era was not limited to the Earth's surface. It extended deep down into the cool interior of the planet, where temperatures were much more stable and where life-saving moisture could be found even in the midst of the most severe drought. The plant world also underwent colossal changes during this era. The disappearance of the great Carboniferous swamp forests cleared the way for a new type of plant, gymnosperms, that reproduced using seeds rather than spores. These newcomers proved far more resilient, able to survive in arid climates and poor soils. Conifers, cycads, and ginkgos triumphantly marched across Pangea, forming dense forests in wetter regions and sprawling woodlands elsewhere. Their seeds, carried by wind or water, could travel vast distances, allowing them to rapidly conquer new territories. Their powerful roots, like steel reinforcement, held the soil together, protecting it from erosion, while fallen needles and cones fertilized the earth. Thus, these plants didn't simply create habitat for animals, they actively changed the very face of the planet. The boundaries of the giant supercontinent were never static. Sea levels rose and fell, driven by global temperature changes and the growth of polar ice caps. When the ocean advanced, it flooded coastal plains, creating vast, shallow inland seas teeming with life. And when it retreated, it left behind thick layers of sediment, chock full of fossils, for future generations. These ebbs and flows were like the breath of the earth itself, and each cycle marked the establishment of a new balance between land and sea. The creatures that inhabited these ever-shifting coastlines were forced to constantly adapt. Some developed life cycles strictly tied to the rhythm of the tides. Others, depending on the season, undertook enormous migrations inland or retreated into the sea. The shores of Pangea never knew rest. They were dynamic zones where life teemed in a state of constant transformation. The air on this ancient world was clean, dry, and saturated with dust, lifted by winds from the lifeless depths of the continent. These winds tirelessly sculpted sand dunes and eroded rocks, but they also served as a means of transport for life. Microscopic travelers, spores and pollen, floated on the air currents, carrying plant genetic material across vast distances, linking ecosystems separated by hundreds of kilometers of land. Global atmospheric circulation connected coastal forests with inland deserts and mountain ranges with endless plains. The same winds that brought devastating dust storms also carried the seeds of new life. Even in the most inhospitable corners of the planet, life found a way to expand its domain, using the very breath of the planet as a means of transportation. Millions of years passed, and Permian ecosystems became increasingly complex and multifaceted. Food chains lengthened and new life forms emerged. Various species occupied previously empty ecological niches. The relationship between predators and their prey evolved into a complex, perfectly balanced dance of death and survival. The abundant vegetation along the coasts provided sustenance for vast herds of herbivores, which, in turn, served as food for large predators. In the deserts, conversely, resource scarcity severely limited population sizes, maintaining a delicate balance in the system. Life adapted to both abundance and scarcity, inscribing itself within the patterns traced by the Earth itself. In any environment, survival was paramount, and the decisive factor was not only brute force, but also the ability to react promptly, hide, or simply endure. Paleontological finds from that era represent more than just fossilized bones and shells. they capture the very behavior of ancient creatures. Trackways reveal animals moving side by side, suggesting the existence of herds or family groups. Tail and even belly marks are sometimes preserved alongside paw prints, revealing the texture of the ancient soil. In some deposits, the specific arrangement of bones clearly indicates the presence of a burrow or den. These fossilized footprints tell stories of a life full of movement, of creatures navigating a landscape that was simultaneously grandiose and intimately familiar. Every paw print, every trace of a fallen leaf, or every ripple on the surface of a dried-up pond is a frozen moment in the life of Pangea. Life on the supercontinent was astonishingly diverse. However, even when ecosystems flourished, the Earth's deep forces continued to shape their fate. Slow movements in the mantle caused entire sections of the Earth's crust to rise and fall, leading to changes in sea levels and triggering massive volcanic activity. Eruptions released enormous volumes of gases into the atmosphere, influencing the climate, triggering periods of global warming or, conversely, cooling, completely altering the environment. All the planet's systems were tightly interconnected, and no event occurred in a vacuum. The creatures of the Permian period were an integral part of this gigantic mechanism. The planet was constantly changing, and life adapted not only to the new geography, but also to the new atmospheric chemistry and temperatures. This delicate balance was maintained for millions of years. Lush forests and fertile plains stretched along the edges of the supercontinent, while the interior remained a realm of deserts and sparse life. The oceans teemed with diversity, and the air above them carried dust or life-giving rains. It was a vast and diverse world, united under a single sky. Life clung to every ledge, every slope, every riverbank, wherever it could find a way to survive. An invisible boundary lay between abundance and emptiness. It wasn't a specific location, but the state of the entire planet, a balance between extremes, where survival meant adaptability and endurance. And although the Earth seemed immutable and eternal to any living creature walking its surface, deep within, slow but inexorable processes continued. The heat rose ever higher. The pressure beneath the Earth's crust grew. The very forces that had once held Pangea together were now quietly preparing to tear it apart. Life, thriving on the surface, unaware of these titanic movements, was part of this grand story. Every plant absorbing carbon from the air, every animal exhaling it, every grain of sand carried by the wind, all were part of a single breath, a global cycle that defined the very essence of the era. The world had reached its maximum scope, while on the surface life continued with calm determination, adapting to the vast expanses and shaping a planet that would soon begin to change as the pressure from within became unbearable. The forests that once covered the coasts and lowlands of Pangea were transformed beyond recognition. The era of dense green canopies and swampy river valleys slowly gave way to a world of aridity and dust. The planet took a new breath, and the world was transformed once again. The heavy rains that once fed full-flowing rivers became rare, and the stable warmth that supported countless creatures began to fluctuate wildly. The air became drier, and the forests lost their former moisture. The balance that allowed them to thrive was disrupted. But even in the harsher climate, the forests didn't give up without a fight. They adapted to new heat waves, fires, and water shortages that engulfed the globe. Only the most resilient trees, hardened by even more ancient worlds, remained in this new, harsh land. Conifers, with their thick, fire-resistant bark and deep roots, dominated regions that could still retain water. Their needles were remarkably resistant to evaporation, and their winged seeds were designed to be carried by the wind for miles in search of a new patch of land capable of bearing life. Cycads, with their sturdy trunks and crowns of tough leaves, grew in clusters where groundwater still lingered beneath the surface. The face of the earth was changing before our eyes. Dense stands of ferns, clinging desperately to the banks of rivers and lakes, created entirely new ecosystems. Each season, in the few places where moisture still remained, the succulent leaves of these ancient plants emerged, forming the foundation of new, more resilient forests. They were sparse but incredibly resilient, able to withstand long months of drought. Now, the cycle of fires began to shape these landscapes, burning away all that was weak and leaving only the strongest. The planet was entering a new, fiery era, the likes of which it had never known before. Imagine, the air became increasingly dry, and the oxygen concentration in it reached levels almost comparable to today's. Under such conditions, any forest turned into a powder keg. Forest fires ceased to be a rare disaster and became an integral part of the landscape. A single spark was all it took. At the height of the dry season, the skies opened up, and a lightning bolt, like a fiery whip, lashed the parched earth. This was enough to ignite a gigantic bonfire, engulfing entire forest tracts. The flames, like a living monster, roared through the forest, devouring everything in their path, from dry grass to the lower branches of the trees. The fire moved with incredible speed, consuming all surface vegetation, leaving behind only blackened, smoking trunks and a thick layer of ash. But here's the amazing thing. This all-consuming, destructive force was not an end, but a beginning. Fire became a great engine of renewal, a cruel but necessary mechanism of rebirth. The unbearable heat destroyed old, diseased growth, and with the ash, valuable nutrients returned to the soil. The scorching air caused the cones of some ancient conifers to burst, releasing seeds that found a new home in the enriched soil. The forests of this era were not simply a static collection of trees, they lived in an eternal, pulsating cycle of fire, death, and rebirth. After the flames died down, the landscape changed dramatically. The charred skeletons of trees didn't stand for long as silent monuments to their former glory. Soon, wind and rain brought dust, which covered the ashes. The tiny particles suspended in the air after the fire were rich in minerals, and as they settled, they fertilized the earth. Months passed, and life itself began to celebrate its victory. The first green shoots emerged from the ashes. Moss covered the burned areas like a velvet carpet, and insects and small reptiles settled in the hollow tree trunks, returning to hunt and hide in the young growth. This scenario was repeated again and again in different corners of the supercontinent, slowly but surely turning fire into part of the very rhythm of life in the prehistoric forest. However, in the very heart of the giant continent of Pangea, a different, far more severe drama unfolded. Here, far from the oceans, rainfall was catastrophically low. Fires flared up more frequently, raged more intensely, and lasted much longer. When centuries-old trees died, new ones didn't always take their place. Dead trunks dried out under the merciless sun, turning to dust. Powerful winds picked up the light wood debris and carried it away, leaving only small fragments mixed with sand and silt. Over millions of years, these remains became part of the thick red sedimentary layers that to this day serve as the hallmark of the interior of ancient Pangea. These scarlet cliffs are silent witnesses to a world that was not a lush paradise, but a harsh arena of struggle for survival, where forests desperately clung to life and dust became the dominant element of the landscape. Dust was the true master here, omnipresent, relentless. It settled like a thin veil on the leaves, thickened the air to the point of fog, and was carried by the winds across entire continents. When monsoons rose over the coast, they captured billions of tiny grains of sand and carried them inland, where they settled on cliffs and in valleys. Each such speck was a fragment of the history of this cruel world. This dust, carried from distant mountains, reflected the dim light of the sun. During the day, it acted as a giant shield, slightly cooling the surface, and at night, conversely, it turned into a blanket, trapping heat near the ground. Thus, unnoticed by anyone, it influenced the global climate of Pangea. This cloud became part of the sky itself, creating a perpetual haze that blurred the horizon and colored the sunlight in alarming reddish hues. Even in the most remote forests, where rivers still murmured, dust settled on the needles of coniferous trees, dulling their natural greenery. The insect world quickly adapted to these new, harsh realities. Their lives became intimately linked to fire and dust. Entire armies of beetles and giant cockroaches found their home in the dry carpet of fallen leaves, tirelessly processing rotting wood and other organic matter. Termites emerged, evolving to digest the tough, wire-like pine needles and tree bark, becoming key scavengers in this ecosystem. Their countless tunnels, penetrating the soil, created natural ventilation, allowing the earth to breathe and remain fertile for the roots of new plants. Pollinating insects were already performing their important work, but pollen transfer still depended not on the bright flowers that didn't yet exist, but on gusts of wind and random movements. The interactions between the insect and plant worlds became increasingly complex, laying the foundation for future ecosystems, where flowering plants would one day rule. But for now, the forests of the Permian period were distinguished by their harsh simplicity and incredible resilience. Each species was focused on one thing: survival in this merciless world. The animals that inhabited these forests led a nomadic lifestyle, following the changing seasons. Enormous herbivores had to make do with the tough leaves of cycads and the delicate shoots of young ferns. Some evolved powerful jaws capable of crushing coarse plant fiber, while others relied on their impressive size and endurance to cover vast distances in search of food. Predators glided in their wake like shadows, ambushing at rare water sources or hiding in the shade of trees where the scorching heat was less intense. Smaller hunters, masters of camouflage, blended with the bark and foliage to strike quickly and disappear. Life here demanded the utmost precision. Every move was honed, every resource utilized to maximum advantage. The presence of fire shaped the behavior of animals no less than it did plants. When a column of smoke rose on the horizon, it was a signal to panic. Vast herds would flee, rushing toward rivers or open plains, away from the flames. Those who could burrow underground waited out the catastrophe in their burrows, sheltered from the deadly heat. When the fire died down, they returned to a completely transformed world. The ash-strewn earth was rich in minerals, attracting hordes of insects, and with them, those who fed on them. The smell of smoke became a dual symbol. It signified both mortal danger and imminent renewal, a constant reminder of the delicate balance between destruction and creation. Over time, many species learned not to fight fire, but to live with it. Their instincts obeyed the same great cycles that governed the entire planet. These ancient forests also preserved the memory of even older worlds. Once, in the Carboniferous period, giant forested swamps were the lungs of the planet. They greedily inhaled carbon from the air and buried it underground, turning it into mighty coal seams. But by the time of Pangea, these wet worlds had disappeared, giving way to arid plains and plateaus. The remnants of those ancient forests, unable to adapt to the new climate, now became fuel for fires themselves. As they burned, they released the carbon accumulated millions of years ago back into the atmosphere rather than storing it underground. Earth's atmosphere responded immediately. Its chemical composition shifted again. The delicate balance between oxygen and carbon dioxide was disrupted, leading to dramatic fluctuations in temperature and precipitation. Fire was both a symptom and a cause of these changes, reflecting dramatic shifts in the exchange of substances between life and the air. Where the landscape was dotted with volcanoes, the connection between fire and life was even more obvious. Eruptions spewed tons of ash into the sky, which traveled for hundreds of kilometers, blanketing forests and plains alike. This volcanic material had a remarkable property. It preserved everything it hid beneath, sealing leaves, branches, and even paw prints in exquisite detail. The layers of this ash that paleontologists find today are frozen moments in time, a kind of prehistoric photograph. In them, we see scorched lands, rivers that had not yet dried up, and animals walking along trails that would soon be buried forever. But volcanic activity did more than destroy. The ash enriched the soil with nutrients, stimulating vigorous vegetation growth after the eruptions ceased. So the fire coming from the depths of the earth could destroy life, but it also supported it, returning valuable minerals to the surface. The interaction of dust and fire created unique patterns across the supercontinent. Regions located near mountain ranges contained more volcanic ash and fertile sediments, allowing dense forests to grow. Meanwhile, inland areas, far from these sources of life, remained barren and dry. Wind, transporting tiny particles from one region to another, linked these ecosystems with invisible threads. The global movement of dust even affected the oceans. Settling on the surface of the giant ocean of Panthalassa, the dust carried trace elements such as iron, which served as food for plankton, the foundation of marine food chains. This great cycle of erosion, transport, and deposition linked land and sea, proving that even in arid conditions, the supercontinent supported life far beyond its borders. For animals dependent on forests, a time of uncertainty ensued. A changing climate forced them to migrate constantly, chasing the retreating greenery. Some species adapted, developing greater mobility, better heat tolerance, or more efficient methods of conserving water. But others simply vanished along with their homes. The fossil record clearly reveals this. We see alternating layers, some brimming with herbivore fossils, while others are virtually empty, preserving only the remains of the most resilient desert dwellers. This pattern reflects the long, slow breathing of the Earth, the inexorable alternation of periods of prosperity and decline that shaped all life on the planet. This is the story frozen in the crimson rocks we find today. Their rich red color is more than just paint. It's a record of oxidation. Iron minerals, exposed to the air and brought to the surface, slowly reacted over millions of years. This color has become a symbol of drought, heat, and soil that rarely saw rain. It also hints at the atmosphere in which these great changes took place. Imagine a world where red dust storms were more common than rain clouds. Consider these majestic scarlet cliffs that today rise in the American Southwest, the unforgiving deserts of North Africa, or the vast expanses of Asia. Before us is more than just stone. These are fragments, frozen in time, from the very heart of the gigantic supercontinent Pangea. They are the legacy of ancient, scorching deserts and parched forests, fused by time into a single, indestructible monolith. These cliffs are silent chronicles of a world that endured eons of total devastation, then cooled and was reborn from the ashes. Its appearance was constantly reshaped by two powerful forces, all-consuming flame and inexorable erosion. But despite all these cataclysms, life on the planet stubbornly clung to existence. Ancient forests drifted with the movement of tectonic plates. Their seeds, caught by the wind, colonized new lands, while old groves withered and turned to dust. In those rare eras when the climate became wetter, in regions adjacent to the jagged coastline of the ancient sea, forests still rose to dizzying heights. They provided shelter for rivers that snaked through fertile valleys. Where precious moisture was preserved, ecosystems were reminiscent of bygone centuries. They were lush, green, and literally teeming with life. Amphibians and ancient reptiles shared these fertile oases, and the air hummed with myriad insects. However, stepping deeper into the vast continent, the struggle for survival took on a completely different, desperate character. Every tree that dared to grow here stood alone against the parching winds and abrasive dust, digging its roots into the rocky, dry soil. The sounds emanating from these forests had nothing in common with birdsong or the soothing rustle of leaves. Rather, it was the low, guttural rumble of the wind and the occasional dry crackle of a tree ignited by the heat. The transition from the green zone of life to the red zone of death, from forest to desert, was not smooth. It rolled in waves, its boundaries dependent on latitude, altitude, and unique local conditions. Some regions experienced temporary relief when monsoon rains returned for a few centuries, or when mighty rivers suddenly shifted their courses, bringing with them new water and life. Others remained waterless deserts for millions of years. The planet's climate cycles operated on a scale incomprehensible to the creatures that inhabited it. What seemed like an eternal, endless drought for one generation was in fact only a tiny episode in the grand drama of changes in the Earth's atmosphere and oceans. These forests of fire and dust were simultaneously fleeting and eternal. Fleeting in their specific forms, but eternal in the very cycle of their existence. While Pangea slowly aged, the deep forces that had created it never ceased their work. The molten mantle beneath its crust continued to churn, press, and shift, creating new zones of crustal uplift and troughs. Volcanic activity continued unabated along the edges of the supercontinent, releasing gases into the atmosphere that directly affected global temperatures. Carbon, released by eruptions and endless fires, accumulated in the air, and the climate shifted again. Each such change triggered a chain reaction, creating an inextricable link between land, atmosphere, and ocean. Forests, as always, responded to these challenges. They adapted, burned to the ground, grew back, and conquered new territories. Dust continued to rise into the sky, carrying particles of dead land far out to sea. And the planet itself, in its slow but steady rhythm, continued to breathe despite all these upheavals. This perpetual movement had its own harsh beauty, albeit devoid of peace. Prehistoric forests were not cozy and hospitable places. They were the arena of brutal struggle, where survival itself depended on forces far greater than any living thing. But from this struggle emerged astonishing resilience. Every seed that managed to take root, every tree that reached for the sun, every insect that found food and took flight, all were part of a great experiment in endurance. Fire cleared space for new life, and dust fertilized the soil with minerals. Together, they created a delicate balance that allowed evolution to continue. These forests of fire and dust were simultaneously a consequence of destruction and a source of renewal. They were the planet's response to change, a constant reminder that even in a world of total scarcity, there is room for growth, and that even in the flames of fire lies the hope of rebirth. And while the landmass of Pangea was scorching and vast, the surrounding waters told a very different story. The supercontinent may have bound the entire terrestrial landmass into a single fist, but in doing so, it gave birth to an ocean that seemed truly limitless. This ocean, Panthalassa, covered almost the entire remaining surface of the planet. It was a global sea, enveloping the single landmass like a gigantic blue atmosphere. It was deep, restless, and full of brutal contrasts. Scorching shallows and icy abysses, lazy currents and furious storms, regions where life teemed and others where it faded in near total silence. The oceans of that era were a world of extremes, heat and cold, creation and decay, and it was in their depths that the great story of life unfolded. Panthalassa's surface was shaped by the wind and temperature. Air, heated over the scorching land, surged upward, drawing in cooler air masses from the sea. This created colossal currents that encircled the entire globe. These currents carried heat from the equator to the poles and returned cold water along the ocean floor, creating a global circulation system that linked all corners of the world's oceans. The temperature differences between regions were enormous. Near the equator, the water shimmered in the rays of the eternal sun, warm and brimming with plankton. Further away, at the poles, ice formed along the edges of the sea, reflecting sunlight back into space. Between these two extremes lay transition zones, where life seamlessly shifted from tropical abundance to polar austerity. The ocean was seething with an endless flow of energy that circulated between the surface and the depths, heat and cold, air and water. The shores of Pangea were the boundary where these two worlds met. To the west, giant waves crashed against the rocks of young mountain ranges, grinding them into tiny particles that nurtured life in the shallows. And to the east, the Tethys Sea cut into the land, forming a long, warm bay surrounded by reefs and mangrove forests. These shallow zones were veritable cradles of life, thriving thanks to the stable sunlight and constant flow of nutrients. Coral-like organisms built reefs that stretched for kilometers, creating complex underwater labyrinths that sheltered countless creatures. Fish darted among the coral branches, ammonites hovered above with their twisted shells, and sea lilies, or crinoids, waved their tentacle-like arms, catching passing prey. The reefs were the true metropolises of the prehistoric ocean. These coral cities were dense, active, and interconnected communities. Every organism depended on the others, on their waste, their movements, their very presence. The water here was crystal clear, allowing sunlight to penetrate to great depths and support photosynthesis. Algae and cyanobacteria formed the base of the entire food chain, converting sunlight into energy and oxygenating the water. Microscopic plankton fed on them, which in turn became food for larger creatures, small crustaceans, fish, and, finally, top marine predators. Sharks patrolled the reefs and waters of the continental shelf. Their sleek, streamlined bodies were perfect hunting machines. Some grew to monstrous sizes, capable of tearing anything smaller to shreds. Others specialized in hunting shellfish or smaller prey. The seafloor of that era harbored an incredible diversity of life. The ocean's biodiversity was truly staggering. Numerous species began to evolve, diverging from the primitive forms of the early Paleozoic. The Permian Ocean was an ecosystem in a state of great transition. Ancient evolutionary lines were dying out, while new ones were just beginning their journey to dominance. But beneath the surface, where not a single ray of sunlight penetrated, the ocean transformed into a completely different world. The deep waters of Panthalassa were cold, still, and often completely devoid of oxygen. The lack of proper circulation in some regions meant that the water at the bottom could remain trapped for centuries, even millennia. In these dark depths, the decomposition of organic matter falling from above consumed the last vestiges of oxygen, creating vast, deadly zones where life was virtually impossible. The sedimentary rocks that formed there eventually turned into dark layers of shale, rich in carbon and sulfur. Geologists still find these strata today as evidence of that ancient era. The deep sea was almost completely still, yet even in these inhospitable conditions, some organisms found a way to survive. Bacteria, capable of existing without oxygen, thrived in the sediments. They learned to feed on sulfur compounds and produce chemical energy that other microorganisms could use. Life adapted to even the most extreme conditions, turning the deadly lack of oxygen to its advantage. Closer to the coast, the seafloor was dynamic and bustling. Mollusks such as brachiopods covered the sandy bottom in a dense carpet, using their valves to anchor themselves or burrow into the sediment. Trilobites, once the most common marine animals on Earth, were gradually losing ground, but some species still clung to life in their ecological niches. New groups of crustaceans and echinoderms took their place. Starfish and sea urchins slowly crawled over rocks and corals, their movements leisurely but constant. Mollusks grew new, stronger shells, and their spirals and ridges were created by nature to protect them from predators and the crushing force of waves. Imagine the seafloor of that distant era. It was not a dead and silent desert. Instead, before us unfolds a seething kaleidoscope of life, where every tiny grain of sand is in constant motion, disturbed by myriads of living creatures. In the shadow of the gigantic world ocean of Panthalassa, there existed a smaller sea known to us as Tethys. While its size was not as staggering as Panthalassa's boundless expanse, its role in the planet's global ecosystem was colossal. Its warm, relatively shallow waters became a vital bridge connecting tropical and subtropical zones. It was a great waterway, stretching from east to west. The powerful currents that swept through its vastness acted like a circulatory system, delivering valuable nutrients and spreading new life forms for thousands of kilometers around. Along its coasts, gigantic reef systems flourished. They acted as natural filters, trapping sediment carried by raging rivers from the continent. Behind these barriers, quiet, serene lagoons formed, a veritable paradise and nursery for countless marine creatures. These protected waters provided a safe haven for juvenile fish and fragile invertebrates, saving them from the ruthless predators that prowled the open ocean. The Tethys Sea also boasted vast underwater meadows of giant algae, forming dense, undulating carpets near the surface. During the day, absorbing sunlight, they oxygenated the water through photosynthesis, and as night fell, they began to respire, reabsorbing the oxygen. This daily pulsating rhythm influenced the entire chemistry of the sea, creating the effect of a giant, slow inhalation and exhalation that echoed the great cycles of the planet itself. The ocean's chemical composition was directly dependent on what was happening on land. The great supercontinent Pangea was not static. Its movement caused increased erosion. Young mountain ranges, not yet smoothed by time, continually released their riches to the sea. Rivers carried calcium, iron, and phosphorus into coastal waters, creating a veritable feast for plankton and stimulating the rapid growth of coral reefs. However, this process also had a dark side. It was precisely this abundance that made the oceans extremely vulnerable to periods of stagnation when the water was deprived of oxygen. When all this organic matter, these trillions of plants and animals, died and sank into the ocean depths, the process of their decomposition consumed oxygen much faster than photosynthesis could replenish it. This cycle repeated itself over millennia, creating a fragile system where incredible abundance could at any moment turn into total scarcity. The ancient seas of the Permian period were fabulously rich, yet they were also in a precarious state of equilibrium. The fine line between prosperity and extinction could be crossed at any moment. Monstrous storms regularly raged along the edges of the gigantic supercontinent. The enormous temperature difference between the scorching land and the cooler sea generated extreme weather events that literally boiled the surface waters. Waves of incredible height crashed with a deafening roar onto the coastal cliffs, reshaping them century after century. Billions of salt spray were carried inland by the wind, nourishing the narrow strips of wild vegetation that desperately clung to life along the shore. But these storms brought more than destruction. They played a vital role in ocean circulation, mixing water layers and bringing nutrient-rich silt from the seabed to the surface. After each storm, when the elements subsided, the water cleared and life, with renewed vigor, resumed its eternal cycle. The ocean's turbulence was more than just chaos. It was a time of renewal, a reminder that energy and movement themselves underlie the stability of our world. In shallow waters, where sunlight penetrated freely and met with abundant nutrients, the diversity of life continued to grow exponentially. Simple sponges, for example, performed a vital function, filtering water and creating the foundation for many reef ecosystems. But cephalopods, the early ancestors of modern squid, had already mastered jet propulsion for lightning-fast movement through the water. Their developing intelligence markedly distinguished them from most other inhabitants. Some of these creatures protected themselves with durable shells, while others, lacking armor, relied on their speed and intelligence, their best defense. Among them, darted fish encased in armored scales, and others with more sophisticated streamlined bodies, harbingers of the fearsome predators of future eras. Every movement, every adaptation was a response to the same harsh laws of survival. Find food, avoid becoming food for someone else, and have time to leave offspring before the merciless ocean takes your life. Pangea was both a cradle and a prison. The distances were so vast that species living on one side of the ocean could evolve completely independently from their counterparts on the other side of the world. Reefs near the hot equator were strikingly different from the colder, more barren ecosystems at the poles. And yet, Everything in this world was connected by a slow but steady flow of water and heat. Nutrients released from decaying remains in one region could, a century later, trigger a burgeoning plankton bloom half a world away. This entire gigantic system represented a global energy conveyor belt, driven by the sun's heat and the planet's rotation. Even in its most tranquil moments, the ocean was never truly still. As the tides receded along the coasts of Pangea, they left behind visible evidence of this perpetual movement. In the lowlands where water lingered, mudflats formed, dotted with traces of the life that had teemed there. Animals that inhabited this boundary between land and sea left footprints and body prints, which the waves covered in fine ripples of sediment. Over time, these fleeting traces became buried under new layers of silt and sand, turning to stone and forever capturing a single moment in the life of that transitional era. The boundary between ocean and continent itself constantly shifted, but the rhythm of the tides remained constant. It was like the beating heart of the planet, measuring the passage of time with a precision that any clockwork mechanism would envy. The chemical composition of seawater during the Permian period was also different than in earlier times. The concentration of calcium and magnesium directly influenced the types of shells and skeletons that living organisms could form. Due to changes in the ratio of these elements, some coral species declined, giving way to other, more adaptable ones. In hot, enclosed basins near the equator, water evaporated rapidly, leading to salt crystallization. This formed thick layers of minerals that, millions of years later, would become rocks, becoming a source of resources for future civilizations. These salt plains and shallow seas were the scene of a fascinating interplay between climate and geology. The eternal dialogue between evaporation, precipitation, and the movement of tectonic plates tirelessly shaped the appearance of this unique world. And there, far from the shores, in the boundless expanses of the open ocean, an all-consuming sense of infinity reigned. The horizon merged with the water on all sides, and there was not a single hint of land. During the day, the sun blazed the ocean's surface, but at night the temperature plummeted. With no continents to smooth out these differences, the temperature difference between the surface and the depths was colossal. The creatures that inhabited these endless aquatic deserts were perfectly adapted to solitude and incredible endurance. Many migrated thousands of kilometers, following currents to their breeding grounds. Others inhabited the twilight zone, where light was fading, but life still desperately clung to existence. Here, in these bottomless depths, a veritable light show unfolded. Bioluminescent organisms pierced the eternal darkness with their living lights, creating a fantastical picture of a starry sky in the ocean abyss. Every flash in this impenetrable darkness carried meaning. Perhaps it was a signal intended to attract a mate, or a cunning trick to blind and confuse a sneaking predator. Their flickering was the only source of light in this murky realm, and it was silent proof that even in complete isolation and eternal darkness, life found a way to thrive. The unified global ocean exerted a profound influence not only on the climate, but also on the distribution of storms and the changing seasons. Panthalassa, with its incredible heat capacity, acted as a gigantic thermoregulator for the planet. It absorbed excess heat during hot periods and slowly released it during cold periods. But this same property also led to truly extreme weather in some regions. The ocean's immense size allowed storms to gain monstrous, unimaginable power before they reached the shores. Waves as tall as multi-story buildings crashed onto the coastline, throwing debris and sea creatures far inland. Each such hurricane redrew the coastal map, crushing cliffs, carving new sandbars, and leaving behind the scars of its destructive force. Along the coast, living organisms adapted to the constant fluctuations in salinity and water level. Some amphibians began spending increasing amounts of time on land, taking advantage of the opportunities afforded by low tide. Some fish developed more powerful fins that helped them crawl from puddle to puddle, and even primitive lungs that allowed them to breathe atmospheric oxygen. These were pioneers, the harbingers of future land animals. These slow, gradual changes laid the foundation for the coming great expansion of vertebrates onto land. The ocean, which seemed a separate world, in fact became the cradle of all the great dynasties that would one day conquer the continents. At the bottom of the Pangea Ocean, enormous yet invisible changes were also taking place. Along the mid-ocean ridges, hot magma rose from the mantle. It cooled, forming new oceanic crust and pushing apart older sections of the ocean floor, and at the opposite edges of the plates, the old, heavy crust slowly sank back into the Earth's depths in deep-sea trenches, remelting into the mantle. This great cycle, hidden from the eyes of living beings on the surface, maintained the planet's internal balance. It was a deep-seated engine that caused continents to drift, mountains to rise, and oceans to change their contours. All life on the surface, without realizing it, depended on this invisible tectonic breathing. At the edges of the supercontinent, the ocean's influence extended far inland, bringing moisture and rain. Powerful monsoon systems, generated by the temperature difference between the continent and the sea, created entire ecosystems. During rainy seasons, rivers overflowed their banks and carried tons of organic-rich sediments to the coast. This nutrient-rich cocktail entered the sea, forming the basis for thriving marine food chains. During periods of severe drought, gigantic dust storms rose above the cracked land. They carried billions of tiny particles in the opposite direction, from the land to the ocean, where they settled to the seafloor. Thus, a continuous exchange occurred, an eternal cycle of matter and energy, constantly flowing in both directions. Let's travel back millions of years and imagine this leisurely dialogue of the planet itself. A conversation between rock and salt, between air and water. The ancient oceans of that time, which we call Pangea, were a wondrous place where abundance and mortal danger coexisted. On the one hand, they supported a richness of life unseen by most previous eras. On the other, they were always on the brink of disaster, on the edge of a knife. The balance between oxygen and carbon dioxide and between temperature and water circulation was incredibly fragile. The slightest deviation in any of these parameters could trigger a chain reaction with dire consequences. These oceans, stretching from pole to pole, teemed with astonishing life, but beneath the water, powerful geological forces continued to operate, the same ones that once held the supercontinent Pangea together. Unbeknownst to all life, volcanic activity and seafloor movements slowly but surely altered the water's chemistry. These gradual transformations accumulated over millennia, setting the stage for future global upheavals unimagined by any living creature. For now, the oceans were full of movement and power. They represented an incomprehensible force that carried the planet's energy from one corner of the world to another. Every wave that crashed onto the shore was invisibly connected to another wave on the opposite side of the globe. Every current that rose from the dark depths carried within itself the memory of the warmth of distant latitudes. Pangea was more than just a gigantic body of water. It could be compared to the planet's circulatory system, its relentless movement, the pulse of the Earth itself. And there, on its shores, where the sea met the land of Great Pangea, life flourished in an eternal cycle of creation, death, and rebirth. And so, beneath the boundless horizon, hidden from view beneath the Earth's smooth surface, history begins anew. Long before any creature could have imagined these titanic forces, the planet's depths were in constant motion. The continents of Pangea, seemingly vast and immovable, actually rested on a foundation far less solid than stone. The Earth's crust, upon which mountains rose, deserts stretched, and seas lapped, was but a thin, fragile shell. Beneath it, it concealed a whole world of scorching, slow movement. Deep in the mantle, matter flowed in gigantic currents that rose and fell like the waters of the world's oceans, creating an invisible tide within the planet itself. Every event on the surface, be it a change in climate, the birth of a mountain range, or the emergence of a new sea, was merely the outward manifestation of this deep, powerful impulse. The history of our planet has always been written not only in its rocks, but also in the primordial heat that drove those rocks into motion. When the disparate continents came together to form Pangea, a completely new era in Earth's history began. The planet's internal balance was disrupted. The crust beneath the supercontinent began to thicken as its edges collided and crumpled into giant folds, forming mountains. Subduction zones, where one plate sank beneath another, grew deeper, and the mantle beneath these regions immediately began to react. Where the Earth's crust was pressed downward, the underlying material expanded under enormous pressure and became even hotter. This, in turn, created zones of buoyant upwelling in other places. The Earth's mantle behaves unlike the flow of a liquid. Rather, it is the slow, viscous movement of solid matter under incredible pressure. This process is driven by heat, partly left over from the planet's formation, and partly by the constant decay of radioactive elements dispersed within its depths. This continuous release of energy triggers convection. Hotter material rises to the surface, cools, and then sinks back into the depths, creating gigantic cycles that can last tens or even hundreds of millions of years. And above this slow but powerful engine, the Earth's crust drifts. The planet's crust is broken into many gigantic fragments called tectonic plates. Each plate contains continents, ocean floors, and associated mountain ranges. Where the plates move apart, molten rock rises from the hot interior, forming new crust and filling the gap. Where the plates collide, one dives beneath the other, only to be reabsorbed into the boiling mantle. This continuous process of recycling maintains the dynamism of our planet. Nothing on Earth is truly eternal. Everything is in motion, obeying the great rhythm of the mantle. Even the most ancient rocks on the surface have experienced countless cycles of uplift and subsidence, creation and destruction. Pangea was just one temporary configuration in this endless sequence, a fleeting act in the great geological drama when the plates came together only to inevitably drift apart again. The heat that powers these titanic movements comes from several sources. Much of it is primordial, preserved from the time our planet formed from colliding pieces of space debris more than 4 billion years ago. The energy of these monstrous impacts was locked within the Earth and has been slowly released ever since. Another portion of the heat is generated by the radioactive decay of uranium, thorium, and potassium atoms. As these atoms decay, they release a small but constant amount of energy over incredibly long periods of time. Together, these sources provide enough heat to keep the mantle flexible and fluid. The planet's outer crust cools and hardens, but the layers beneath it remain dynamic and hot. The contrast between the cold, brittle surface and the hot, flexible interior creates tension, leading to cracks and movement. The planet constantly strives to balance its temperature by releasing excess heat. It is this desire that causes continents to drift, oceans to expand, and volcanoes to erupt. During Pangea, this process reached unprecedented intensity. Imagine the supercontinent as a giant blanket that prevented heat from escaping freely from its interior. Typically, when continents are separated, heat easily seeps through the thinner crust of the ocean floor. However, when all the land is gathered into a single mass, the thick continental crust acts as a powerful insulator. Over millions of years, temperatures beneath Pangea began to rise steadily. The mantle beneath its core became increasingly hotter and more fluid, while cooler, denser regions formed at the edges, where old oceanic crust was subducted into subduction zones. This uneven distribution of heat created colossal tension across the entire supercontinent, and although the surface appeared calm, monstrous pressure was building in the inaccessible depths. Volcanic activity along the edges of Pangea was the outward manifestation of this hidden energy. Subduction zones formed where the oceanic plates of Panthalassa and the ancient Tethys Sea sank beneath the continent. As they sank, water and other volatiles were released from the rocks. This lowered the melting point of the surrounding mantle and facilitated the formation of magma. This molten rock rushed to the surface, forming entire arcs of volcanoes that encircled the supercontinent's borders like a ring of fire. Each such eruption released heat, gases, and minerals into the atmosphere and oceans. These gases, primarily carbon dioxide, sulfur dioxide, and water vapor, directly influenced global temperatures and Earth's chemical cycles. Over time, volcanic activity came to play a key role in climate regulation, balancing the cooling effects of rock weathering and the absorption of new greenhouse gases by the ocean. Far from the active boundaries, in the very heart of Pangea, the effects of mantle pulsations were less visible, but no less important. Heat accumulation beneath the center of the continent began to slowly uplift it. Vast tracts of land rose, forming broad plateaus, while the crust in these regions thinned. As a result, faults appeared on the surface, at first barely noticeable cracks that marked zones of future weakness. It was here, in these zones, that the land would eventually begin to stretch and crack. These faults were destined to open only millions of years later, but the process had already begun. The planet was slowly and deliberately preparing for the next phase of its tectonic cycle. Even at its peak, Pangea already bore the seeds of its own destruction. Beneath its seemingly unshakable surface, the process of fragmentation had already begun. One of the most striking evidences of this were earthquakes, echoes of deep-seated activity. Along the boundaries of Pangea's tectonic plates, where compression and subduction occurred, incredible stress accumulated in the rocks. When this stress exceeded the tensile strength of the Earth's crust, it was released in the form of devastating seismic waves, causing the Earth itself to tremble. These events, though brief in geological terms, were part of the planet's constant adaptation to its own internal forces. Vibrations from earthquakes spread through the Earth's interior, revealing to future scientists the Earth's layered structure: crust, mantle, and core. Long after these ancient tremors had died down, their traces remained forever in deformed rocks and fault zones, recording the planet's history. Struggling to maintain its internal equilibrium, the Earth continues to move. As this movement occurs, heat rises from the mantle to the surface, creating conditions conducive to life. This process also influenced the chemical composition of the oceans. At mid-ocean ridges, where new crust was forming, hydrothermal vents, known as black smokers, spewed hot, mineral-rich fluids into the seawater. These underwater geysers were generated by the same convective heat that moved the plates, and they created entire ecosystems that lived in complete darkness, completely independent of sunlight. The microbes that lived there, here in the dead, icy darkness of the ocean depths, where no ray of light ever penetrated, a completely different drama of life unfolded. Life teemed around these hydrothermal vents, these black smokers, spewing boiling water and toxic chemicals from the planet's depths. Instead of solar energy, the local inhabitants learned to harness the chemical power contained in sulfur and methane. These were unique, almost alien-like ecosystems, consisting of giant tube worms, blind crustaceans, and a host of other creatures, perfectly adapted to the eternal night and colossal pressure. These deep-sea oases served as a powerful reminder that life on Earth is not just about what happens on its surface. It is capable of clinging to existence even in the most unimaginable, most hostile conditions. And the source of this life was the same internal heat, the same unstoppable energy that drove the giant continental plates far above. Throughout geological history, this delicate balance of forces determined the fate of the planet. The speed with which continents slid across the face of the Earth was directly dependent on the balance between the release and loss of heat from its interior. In our planet's youth, when radioactive decay in its core was far more intense, the mantle was a seething cauldron. Convection currents within it were furious and rapid. Continents raced across the surface, colliding and breaking apart in a geological dance that took far less time than in later eras. But as the planet aged and gradually cooled, this frantic movement began to slow down. By the time the giant supercontinent Pangea formed, heat release from the mantle was no longer as explosive as it had been in the past. However, its power was still more than sufficient to drive colossal tectonic plates. The emergence of this single landmass was the culmination of a long period of planetary cooling, but it also exacerbated this process. Pangea, like a giant blanket, covered part of the Earth's crust, preventing the internal heat from escaping and trapping it deep within. The planet's pulse became slower, but much deeper, more powerful, and more profound. It's difficult to even imagine the movement of mantle flows due to their inhuman scale and timescale. This process occurs at a rate of just a few centimeters per year. Imagine, this is significantly slower than the growth of a human fingernail. It seems insignificant, almost zero. However, given millions and hundreds of millions of years, this barely noticeable shift is capable of raising mountain ranges from the seafloor, creating bottomless ocean trenches, and shifting entire continents. Deep beneath our feet, the rock behaves not like a solid body, but like an incredibly thick, viscous liquid. It slowly rises where it's hotter and sinks where it cools. These invisible currents transport enormous volumes of heat and matter, continuously mixing the planet's interior and renewing its face. And on top of this grandiose system, like giant rafts in a slow, invisible ocean of molten rock, drift the tectonic plates. Every volcano erupting to the surface, every earthquake shaking the earth, every mountain range reaching skyward, all these are merely the outward manifestations of this hidden titanic movement. This is the physical heartbeat of our planet, a rhythm that has not faltered for a moment for over 4 billion years. The red-hot core, hidden at the very center of the Earth, only amplifies this pulsation, adding its own heat and generating a powerful magnetic field. The outer core is a seething ocean of molten iron and nickel. These streams of liquid metal rotate, creating a gigantic dynamo that generates the Earth's magnetosphere. This invisible shield extends far into space, protecting all life on the surface from the deadly stream of charged particles flying from the sun. It is this field, like a compass, that guides migrating animals on their long journeys. The movement of the core directly influences the mantle above it, and the mantle, in turn, influences the core. These two layers are in a complex interaction that scientists are still trying to unravel, forming a single dynamic system. The energy escaping from the core fuels convection currents in the mantle, and the mantle, like a giant radiator, regulates the cooling rate of the core itself. Thus, the pulsation beneath the continents is not a localized process. It is part of a global cycle of energy and matter that encompasses our entire planet, from its very center to the surface. During the time of Pangea, this magnetic field left its mark, its signature, in the rocks. When lava flows erupted onto the surface and cooled, or when sedimentary rocks containing magnetic minerals compacted, something remarkable happened. As they solidified, tiny particles within them, like compass needles, aligned precisely with the direction of the Earth's magnetic field. They froze in this position forever, preserving information about the location of the magnetic pole at that moment. For millions of years, the continents continued to drift, and the magnetic poles shifted, and these geological records accumulated layer after layer. Today, paleontologists can decipher these ancient records to learn precisely how the continents moved and how the planet's polarity shifted. These rock records not only show us where Pangea once was, but also tell the dramatic story of its slow but inexorable disintegration. The rocks themselves preserve the memory of the planet's invisible pulse. Each layer is a frozen frame, a record of the direction and speed of this great movement. The growing heat beneath Pangea not only transformed the solid Earth beneath, but also influenced what was happening on the surface. In regions of high geothermal activity, where internal heat reached close to the crust, hot springs, geysers, and gas vents emerged, altering the composition of the atmosphere. In some places, these emissions of methane and carbon dioxide, rising from cracks in the Earth, contributed to slow global warming. In others, powerful basaltic eruptions bathed vast territories in layers of molten lava, forming vast volcanic plateaus. Each such eruption released tons of minerals to the surface, which over time enriched the soils and sedimentary rocks. Even the most violent destruction carried the seeds of future renewal. The connection between the planet's internal processes and its biosphere was absolute and inseparable. Heat and gases emanating from the depths fueled chemical reactions on the surface, defining the boundaries of what was possible and creating new opportunities for the evolution of life. As the Permian period drew to a close, the accumulation of heat beneath the supercontinent became increasingly critical. For tens of millions of years, this enormous energy, trapped beneath Pangea, had been building and pressing from within, preparing to tear it apart. It began to force its way upward, creating rift valleys, giant cracks and fissures that would one day become the seeds of new oceans. This process had already begun, albeit almost imperceptibly. The gentle stretching of the Earth's crust, the increase in volcanic activity, all these were the first, barely perceptible signs of things to come. These early rifts were invisible to the dinosaurs and plants that inhabited the surface. They went about their lives unaware of the titanic drama unfolding deep beneath their feet. But from a geological perspective, this was the beginning of the end. The Earth was preparing for the next act of its play, continuing the eternal cycle of assembly and disintegration, creation and destruction. The pulse beneath its surface never stopped, it only changed its focus. On shorter timescales, the planet's internal heat influenced weather and climate through volcanic activity. When major eruptions occurred, tons of sulfur compounds were released into the atmosphere. Reaching the stratosphere, they created a kind of mirror screen that reflected some sunlight back into space and caused a temporary cooling. But then, as carbon dioxide from the same eruptions accumulated in the atmosphere, the climate began to warm again. These fluctuations were insignificant on the scale of geological epochs, but they directly shaped conditions in specific regions and influenced the course of evolution. Every volcanic eruption, every tectonic shift, was a replica in a slow dialogue between the Earth's interior and its surface, between fire and air, between movement and rest. Even today, hundreds of millions of years after the fragments of Pangea drifted apart, the legacy of that ancient pulse is still visible everywhere. Mountain ranges that were uplifted by the collision of continents still stand, albeit worn down to their foundations by wind and rain. Their contours are blurred by time, but their origins cannot be hidden. Volcanic rocks we find at the boundaries of ancient plates bear witness to the powerful flow of magma that once raged here, welding the continents together. Magnetic stripes on the ocean floors tell us the story of how they drifted apart after the Great Breakup. The history of Earth is a story of ceaseless, eternal movement. Each era leaves its imprint on the next. The pulse that once beat beneath Pangea can still be felt deep beneath our feet, as steady and inexorable as it was in those distant times. It is slowly but surely changing the face of our planet. Grain by grain, centimeter by centimeter. To imagine the Earth as a living system is to imagine it in constant motion. The continents in this analogy are its skin or crust. The mantle is its mighty muscles, and the core is its beating, fiery heart. Heat flows through its veins like blood, carrying energy and maintaining a delicate balance. And though the surface may appear still and tranquil to us, deep beneath it, movement never ceases. Pangea was just one phase of this great cycle, one of many breaths our planet takes throughout its incredibly long history. It is an eternal sequence of expansion and contraction. Deep within, like a mighty pulse, beats the very force that gave birth to this world, sustained it, and perhaps one day will bring it to an end. Continents move, oceans are born and die, mountains rise to the sky and crumble to dust. And through all these enormous changes, an invisible but constant flow of heat continues its journey, causing a slow transformation of the planet that never stops changing. The world on the surface, above this churning mantle, lived its own life, as if frozen in slow motion. It was the result of nature's grand experiment in changing climate, temperature, humidity, and winds, swirling endlessly around a single gigantic landmass, Pangea. The climate of that era was more than just a backdrop for life. It was a complex system, full of sharp contrasts, spanning all latitudes from pole to pole and evolving over millions of years. Solar heat and the movement of the Earth's interior shaped this world. Ocean currents and volcanic activity, all of this interacted to create landscapes of such power and scale that no living thing could have created. Yet every living thing was utterly dependent on these harsh natural conditions. The Permian climate was like Pangea itself, a land of extremes, creating thousands of diverse, yet often hostile habitats. When the continents were scattered across the planet, the oceans acted as giant air conditioners, moderating the climate. Sea breezes carried moisture inland, storms poured down torrential rains, and air circulated freely between the equator and the poles. But Pangea completely changed this picture. This enormous landmass, concentrated in one place, created entirely new, brutal rules of the game. Imagine the world united into a single gigantic continent. At the very heart of this colossal landmass, known as Pangea, lay lands forever cut off from the ocean's moderating breath. Air masses, saturated with the moisture of the great ocean, lost their life-giving power long before reaching these inland regions. On the coasts, they poured down torrential rains, but having passed over the coastal mountain ranges, they turned into parching, hot streams. As a result of this monumental natural process, one of the greatest deserts in the history of the planet was born at the center of Pangea. Before us stretches a vast sun-baked plain, hued in shades of red and orange. Along the edges of this supercontinent, where the influence of the sea was still felt, forests rustled and mighty rivers flowed, their existence entirely dependent on the capricious monsoon winds. This unique geography gave rise to unprecedented weather systems. Hot air rising over the scorching land created low-pressure zones that drew in moist currents from the global ocean of Panthalassa and the ancient Tethys Sea. But this moisture reached only the coastal regions. Inland, dry, descending air prevailed, which, as it descended, heated up even more, forming stable high-pressure zones. It was these high-pressure zones that held these gigantic deserts captive. Thus, a distinct system of climatic zones emerged on the planet. Humid tropics at the equator gave way to arid zones, which in turn gave way to temperate forests, and at the poles, ice caps encased the Earth. Global weather as we know it was born from this great exchange of heat and cold. Here, far from the seas, a world of brutal contrasts reigned. The temperature difference between day and night was truly colossal. Without the ocean to act as a natural heat accumulator, the planet's surface behaved differently. With the rising of the sun, the scorching Earth turned into a gigantic frying pan, and the air became thick and scorching. But as soon as the sun disappeared behind the horizon, the heat instantly evaporated, and a piercing cold set in. Precious dew could fall only in the most sheltered lowlands. Life had to adapt to this merciless rhythm. Plants had to become true desert warriors. They grew tough, waxy leaves to reduce evaporation, anchored themselves in the earth with deep roots, and protected their trunks with thick bark. Animal life also obeyed this law. During the hottest hours of the day, all living things froze, hiding in the shadows of rocks or in shallow burrows, and only at dawn or in the deepening twilight, when the unbearable heat subsided, did the hunt and the struggle for survival begin. All life here was a dance on the edge between light and darkness, heat and cold, but a completely different picture unfolded on the coasts of this supercontinent. In those distant lands, the climate was far more varied and mild. The proximity of the ocean moderated the extreme conditions. Here, powerful seasonal winds reigned supreme, bringing life-giving moisture inland, filling riverbeds, nourishing dense forests, and supporting complex, thriving ecosystems. The Permian monsoons were particularly fierce due to the colossal temperature difference between land and sea. During the warmer months, the land warmed faster than the ocean, creating a gigantic natural pump that drew in moist sea air. A season of great rains would begin, which could last for months, turning lowlands into temporary lakes and swamps. With the arrival of cold weather, the pendulum swung back. The winds reversed direction, bringing dry air and cooler temperatures. These great cycles of moisture and drought dictated the laws of all life, determining the growth of plants, the migration routes of animals, and the very existence of entire worlds. The chemical composition of the ancient atmosphere also contributed to this delicate balance. Carbon dioxide concentrations at that time were significantly higher than today. One of the main reasons for this was the incessant volcanic activity along the tectonic faults of Pangea. Volcanoes spewed millions of tons of gases into the air, which enveloped the planet like an invisible blanket. This greenhouse effect prevented heat from escaping into space, maintaining high temperatures worldwide. It was thanks to this warmth that tropical conditions were able to extend far north and south of the equator, allowing life to flourish in areas that would otherwise have been perpetually frozen. However, this mechanism also had a downside. The climate became incredibly sensitive to the slightest changes. As volcanic activity intensified, the planet would literally suffocate from the heat. And when geological processes slowed and weathering rocks began to absorb carbon dioxide from the air, cooling ensued. The Earth's climate has become an arena for an eternal struggle between sources and sinks of greenhouse gases, and the fate of all living things depends on the outcome of this battle. Let's fast forward to the early Permian period. In the southern parts of Gondwana, in the territories that would one day become South Africa, India, and even icy Antarctica, the ghosts of the recent Great Glaciation could still be found. Giant ice sheets left deep scars on the planet's surface, enormous furrows and scratches in the rock, evidence of their slow, inexorable movement. But the climate warmed, and the glaciers began to retreat, revealing valleys and basins that immediately filled with meltwater, giving birth to new rivers and lakes. This colossal volume of fresh water pouring into the oceans slightly altered their salinity and influenced global currents. Gradually, the Ice Age faded into the past. The polar caps remained, but most of the planet was plunged into a long era of warmth that lasted until the catastrophic events that ended the Permian period. This balance between heat and cold was never static. The planet's climate resembled a giant seesaw, tossed and turned by powerful forces of nature. Volcanic ups and downs, subtle shifts in Earth's orbit, and other cosmic factors constantly influenced surface conditions. When major eruptions occurred, not only greenhouse gases, but also sulfur dioxide were released into the atmosphere. Its particles, like tiny mirrors, reflected sunlight back into space, causing a short-term but sharp cooling. But when the dust settled, the accumulated carbon dioxide in the atmosphere took its toll, triggering a new round of long-term warming. Furthermore, over tens of thousands of years, Earth's orbit slowly shifted, altering the angle of sunlight at different latitudes. These great cycles affected precipitation, the boundaries of forests and deserts, and the entire planetary ecosystem. Climate was not a stable given, but a dynamic, ever-changing system. And each such change became an impetus for evolution, forcing some species to adapt, others to migrate, and still others to disappear forever. But perhaps one of the most striking differences in the atmosphere of that time was the composition of the air itself. The air its inhabitants breathed. Long before, during the Carboniferous period, oxygen levels were incredibly high. This was the era of giant insects and vast swamp forests, which gave the planet this excess oxygen. However, over time, the climate became drier, the giant forests began to shrink, and increasingly frequent forest fires consumed oxygen at an unprecedented rate. As a result, oxygen levels dropped almost to modern levels. This global change affected everything, from the respiration of living creatures to the nature of fire itself. Fires now spread more slowly, and their flames were less hot. Among the animal kingdom, those with more efficient respiratory systems and high metabolisms gained an advantage. Others were forced to wage a desperate struggle to survive in the thinner air. This new atmospheric balance was a direct reflection of how the planet itself was adapting to the changing life on its surface. Every breath taken by any creature on Pangea carried echoes of the ancient history of photosynthesis, fire, and decay that created this unique world. The great ocean, lapping the shores of Pangea, was a mirror, reflecting all these complex atmospheric processes. Warm currents, like gigantic rivers, carried equatorial heat to the poles, while cold waters from the polar latitudes returned, creating a global circulation system. This eternal cycle redistributed energy across the planet and directly influenced weather. Where warm, moist waters met cold air, monstrous storms were born, battering the coasts with hurricane-force winds and torrential rains. This perpetual interaction between ocean and atmosphere was the primary engine of the planet's climate machine, and its operation determined whether a given region would become a thriving oasis or a lifeless desert. The Earth itself kept a detailed record of these climatic dramas. We can read this story in the geological cross-sections of that time. The alternating layers of sandstone and mudstone are nothing less than a stone chronicle of the alternation of wet and dry seasons. The coarser, thicker layers of sandstone formed during periods of great rains, when raging rivers overflowed their banks and carried sand across the valleys. And the thin layers of shale are a memory of dry periods, when the waters receded and only the wind carried fine dust from the heart of the deserts. These patterns repeat themselves again and again, representing a unique archive of a great climatic experiment stretching over millions of years. Each layer here is a page of history, telling the story of a season that could last thousands of years, and it was born of the same winds and rains that sculpted the ancient Earth. The plant world reacted sensitively to these changes, undergoing its own quiet revolution. Species that had once thrived in the Carboniferous swamps were now forced to adapt to severe drought. The ancient spore-bearing plants were replaced by gymnosperms, more resilient and sophisticated. Their hard seeds and waxy leaves were ideal weapons in the struggle for survival. Drought-resistant conifers conquered the highlands and plains. Their needle-like leaves perfectly retained precious moisture. In regions with a milder climate, majestic cicadas and ginkgos could be found. Only in the wettest places, near rivers and lakes, did seed ferns still hold their ground. These new plants played a key role in the ecosystem. Their roots held the soil together, preventing it from turning to dust, and continued to regulate the composition of the atmosphere. Through photosynthesis, they greedily absorbed carbon dioxide and exhaled oxygen into the air, maintaining that delicate balance on which all life on the planet depended. Let's transport ourselves to that distant world where life on land obeyed its own, entirely different laws. Animals were forced to migrate, their migrations following the capricious spread of vegetation. Imagine giant reptiles whose survival depended on thickets of pine needles and tough shrubs. They were the living mowing machines of prehistory. And in their wake, across the endless sun-scorched plains, predators stalked relentlessly, awaiting the moment to strike deadly blow. In the drier, more desert regions of this world, a unique drama of survival unfolded. Here, evolution worked to the limit, creating creatures capable of conserving every precious drop of water and withstanding the scorching heat. Some of these creatures found refuge underground, becoming skilled diggers. In their deep burrows, they hid from the brutal temperature swings, from the heat of day to the cold of night. Others, however, took a different path. Over time, their skin transformed into veritable armor, thickening or acquiring a light, almost white color that reflected the sun's merciless rays like a mirror. And on the coasts, at the edges of ancient oceans, life was in full swing. Here, in the realm of humidity, amphibians and aquatic reptiles flourished. They enjoyed the fertile conditions, hunting for abundant fish and myriad insects. The astonishing diversity of life accurately reflected the planet's climatic mosaic. Every corner, every ecosystem was shaped by the unique influences of geography, prevailing winds, and heat distribution. The complex interactions between land, ocean, and atmosphere transformed Pangea's climate into an incredibly sensitive, feedback-driven system. As deserts expanded, their lighter surfaces reflected more sunlight, leading to subtle but global cooling. But as soon as vegetation conquered new territories, the dark greenery began to absorb more heat, which, in turn, triggered torrential rains. These forces constantly balanced each other, but it was precisely this fragile harmony that made the entire system extremely vulnerable to abrupt, catastrophic changes. The slightest fluctuation in average temperature or a single powerful series of volcanic eruptions could completely redraw the precipitation pattern over an area thousands of kilometers long. The climate of ancient Earth was like a taut string. It was a gigantic system of interconnected gears, each component reacting to the movements of the next with a massive delay, sometimes stretching for millennia. And in the most remote southern regions of the gigantic continent, the icy breath of the past ice age could still be felt. Antarctica, firmly anchored to the southern tip of Pangea, was encased in massive ice caps that inexorably advanced and retreated in a perpetual dance with the seasons. Mighty glaciers, like giant chisels, carved deep valleys and fjords into the cliffs, grinding the rocks into a fine powder that raging rivers carried far north. And each time the ice began to melt, it released colossal torrents of fresh water. These torrents reshaped the continent, washed away entire landscapes, and deposited thick layers of silt on the ocean floors. These periodic, great melts directly affected sea levels, causing them to rise and fall over millions of years. The rhythm of this icy advance was excruciatingly slow, yet utterly inexorable. Volcanic gases played an invisible but critical role in this global climate balance. Sulfur and carbon, released into the sky during eruptions, became invisible orchestrators of the planetary climate. Reacting with water vapor and sunlight, they formed the very atmosphere that determined the weather during the Permian. Some of these volcanic substances turned into aerosols, reflecting solar radiation back into space and causing cooling. Others, on the contrary, acted like a giant blanket, promoting long-term warming. The timing and scale of these emissions determined whether an entire region would cool or become a blazing furnace, regardless of whether forests grew or died. Over geological eons, these great cycles created and then completely destroyed entire ecosystems. Their imprints are forever preserved in the fossilized soils and isotopic composition of ancient rocks. The climate of the Permian period was not something static and constant. No, it was a living, breathing, constantly changing system, taking on a new form with every volcanic eruption, with every uplift of a mountain range, and with every thunderstorm that swept across the ancient sky. Even the color of the rocks from that era can tell us an incredible story about the atmosphere. The ubiquitous red deposits, sandstones and mudstones stained with iron oxides, suggest that they formed in arid conditions when the sky was abundant with oxygen. Their characteristic blood-red hue is the result of simple oxidation, planetary rust, caused by the reaction of minerals with the atmosphere. Over millions of years, these rocks formed in conditions of extreme heat and low humidity. Today, we find them on every continent: North America, Europe, Asia, and Africa. These are the remains of the ancient supercontinent Pangea, and they provide irrefutable evidence that the arid and scorching interior of that world spanned vast territories across the globe. The red soil of Perm was the visual embodiment of its climate. It was a world where heat, dust, and oxygen intertwined under the rays of a merciless sun. But even in these harsh, almost Martian conditions, life did not give up. It continued its great struggle. The climate became the greatest test of endurance for every species, favoring not strength or numbers, but the ability to adapt. Only those who could withstand drought, heat, and constant change survived. Species that required stability to thrive were doomed to extinction. Evolution proceeded along its quiet but incredibly effective path, creating living organisms capable of withstanding resource scarcity and the absolute unpredictability of the surrounding world. And these battle-hardened survivors would face even greater trials when the planet's fragile balance would finally be disrupted by the colossal strain on its own systems. But for now, this great experiment continued. A world of heat and dust, monsoons and deserts, oxygen and fire, every element of climate was inextricably linked to every other in a single global network. Mountain erosion pulled carbon from the air and plant growth returned it to organic form. The movement of ocean currents, the redistribution of heat, and continental drift changed the direction of the winds. The entire planet was a single feedback mechanism, constantly adjusting itself, desperately trying to maintain equilibrium. It was an experiment without any purpose or direction, just the natural result of the laws of physics, chemistry, and the vastness of time. And in this endless process, Earth found ways to moderate its own extremes, maintaining itself within that narrow range of conditions that allowed life to persist. And life went on. The climate of the Permian was neither completely hostile nor completely benign. It was a mixture of both, a vivid demonstration of what happens when a planet gathers all its continents into a single gigantic landmass, begins to accumulate internal heat, and its atmosphere acquires its own unique rhythm. Every storm, every drought, every temperature fluctuation was part of this grand process. From the ice-bound poles to the blood-red deserts and the rare green oases on the coasts, the world was exploring the limits of its stability, testing how far it could go before the balance was forever disrupted. This great experiment continued under the same sun that shines upon us today, and the results of this long, brutal ordeal are still visible on the face of the Earth. The world had found its own pulse. A palpable warmth emanated from the planet's surface. Winds swept unimpeded across the vast expanses of the gigantic continent. Rain fell on the coasts, but almost never reached its scorching heart. And life, in its eternal quest for survival, adapted to this rhythm. It was always prepared for the difficulties the Permian world presented, and even in this harsh age, it found the strength to overcome new challenges. Pangea endured the harshest conditions, yet the planet was teeming with life. Even the most inhospitable environments, from parched deserts to shallow seas, teemed with creatures that had learned to survive and thrive. The history of that time is not a saga of rapid expansion and conquest, but rather a chronicle of incredible tenacity. It was a time when living creatures and plants found astonishing ways to adapt to scarcity and constant change without giving up their place in the sun. Ancient forests still stretched across the lowlands and coastal plains, while they were certainly very different from the lush, swampy jungles of the Carboniferous period. They supported a new type of life with remarkable resilience. Conifers, tree ferns, and seed ferns now dominated the landscape. Their powerful roots gripped the soil tightly, retaining precious moisture, while their leaves were narrow and covered with a waxy coating, significantly reducing evaporation. These plants became the foundation of all life on land. The air in these forests was dry and warm, but by no means lifeless. Myriads of insects swarmed everywhere, creating complex ecosystems, providing constant pollination, fertilizing the soil, and decomposing organic matter. Reptiles that climbed tree trunks or hid in their shade found safe refuge among the roots. The trees themselves had evolved to withstand both forest fires and drought. Their thick bark could withstand extremely high temperatures, and seeds were able to germinate even after long periods of dormancy. These adaptations weren't simply a response to the environment, they were an active part of the process, determining how the ecosystem processed nutrients and how fire spread across the land. Among these resilient trees lived representatives of a new dominant order. Amphibians, which had once dominated the Carboniferous period, were now pushed into wetter regions, where streams and ponds provided their delicate skin with the necessary moisture. Their large, flattened heads and heavy, clumsy bodies were living relics of a wetter past. In their place, a variety of reptiles spread across Pangea. They were the first truly land animals. Reptiles became the true masters of the land, learning to live and reproduce without returning to the water. Their eggs were encased in tough, leathery shells that protected the developing embryos from fatal desiccation. And the reptiles' scaly skin reliably retained moisture within their bodies, allowing them to travel vast distances on land, a journey that would have been fatal for their amphibian ancestors. These reptiles exhibited a truly astonishing diversity. Some were small, fast, and insect hunting, moving with remarkable agility across the forest floor. Others were massive, heavily built herbivorous giants that fed on the tough vegetation of the dry plains. Still others evolved into predators, lean, agile, and ruthless hunters who hunted anything smaller than themselves. The division between herbivores and carnivores, between scavengers and ambush hunters, became clearer than ever before. The ecosystems of the Permian period began to increasingly resemble those that would later define the entire age of reptiles, though the creatures themselves were more ancient, bizarre, and unlike anything we can imagine. And among all this diversity, one truly unique group stood out: the synapsids. Although they weren't true reptiles in the strict sense, they had something that would forever change the course of evolution. Take a closer look at these creatures. Their anatomy shares many similarities. Let's go back in time and look at the structure of their skulls. Here, behind each eye socket, we see a single opening. And this wasn't just an anatomical detail, it was their secret weapon, an evolutionary innovation that allowed them to attach incredibly powerful muscles to their jaws. This seemingly insignificant structural feature gave them a colossal advantage. These creatures, synapsids, could grind their food with unprecedented efficiency, extracting maximum energy from it. This allowed them to better control their internal fires and metabolism, leaving their reptilian ancestors far behind. Some of them, as if straight out of a science fiction novel, reached gigantic sizes. Recall Dimetrodon, which carried a huge bony sail on its back, perhaps a natural radiator for regulating body temperature. Others remained small and agile, their bodies covered in smooth skin or the very first traces of protective insulation. In their veins flowed the blood of the future rulers of the planet, mammals, although their era was still eons away. During the Permian era, they were the dominant force among all terrestrial vertebrates, spreading across every accessible corner of the gigantic continent. However, their dominance was not total. Look at the world at their feet. Here, in every corner, a completely different life was teeming. Billions of insects and snails had conquered every available space, creating a unique, buzzing, crawling world where they hovered in the air, dug the earth, slid across surfaces, and participated in the eternal cycle of decay. Beetles, which already roamed the planet, appeared in all their diversity of forms. Their impenetrable shells and perfect wings paved the way for them to thrive in any climate, even the harshest. Dragonflies, though smaller than their giant carboniferous ancestors, still remained formidable masters of the skies. Termites tirelessly destroyed dead wood, and ancient cockroaches performed the same role as their distant descendants do today. All of these creatures formed the foundation of the food chain, processing organic matter and supporting the lives of larger reptiles and amphibians. Their survival depended directly on their ability to adapt to the hot, parching climate. Many species developed ingenious solutions. They grew thicker exoskeletons to minimize the loss of precious moisture, or completely altered their daily routine, hunting only during the cool hours of dawn and dusk. Their life cycles were no longer governed by the changing seasons, but were tied to the daily dance of sun and shadow and fluctuating air temperatures. Along the coasts and in river floodplains, amphibians still clung to life. While their diversity had paled compared to previous eras, their presence was still palpable. Some had evolved into veritable river monsters, occupying the niche of top freshwater predators. Lurking in the shallows, they became living traps, their flat heads and enormous jaws perfectly designed for a surprise attack on any unwary reptile or small animal that came to the watering hole. Other amphibians led a more humble life among the coastal vegetation, hunting insects and using their powerful legs to navigate the sticky mud. But with each passing century, as the climate grew drier, their world collapsed. The ecosystems on which they depended became alarmingly fragile. Ponds and streams could evaporate completely in just a few weeks of relentless drought, condemning amphibians to painful deaths or desperate migrations. Generation after generation, their populations dwindled, retreating to the last bastions of moisture, seacoasts, river deltas, and the shores of large inland lakes. This slow but inexorable retreat became one of the first visible scars left on the face of the planet by global climate change. Meanwhile, life in the world's oceans obeyed its own entirely unique laws. Although aquatic life was a far more stable environment than land, it was no paradise either. The vast ocean of Panthalassa was uneven, its waters circulating poorly. Some corners teemed with life, while others were vast stagnant zones deprived of oxygen. Shallow sea creatures thrived where sunlight and nutrients were abundant. Here, sponges built vast reefs, home to countless marine creatures. Bryozoans and the first corals formed the foundations of these underwater metropolises, while myriads of fish hovered in the waters above. Sharks, bony fish, and armored fish all traced their ancestry to even more ancient forms. Ammonites, drifting slowly in the currents, built their twisted shells, which in themselves were a chronicle of their leisurely, centuries-long journey. But even in these fertile waters, a constant struggle for survival raged. Species constantly devised new hunting strategies, new modes of locomotion, and new armor to protect against predators. The ocean, like the land, was in a state of perpetual transition. And in the deep, dark waters, life abandoned the sun's energy altogether, finding another source. Here, along mid-ocean ridges, hydrothermal vents spewed heat and nutrients into the water. Bacteria took advantage of this, learning to feed on the minerals in the hot streams. These microbes, in turn, became the basis for entire communities adapted to the eternal darkness and colossal pressure. Crustaceans, giant tube worms, and mollusks thrived in conditions that would have instantly killed most other life forms. Their existence is a testament to the incredible resilience of the biosphere. Even in the most extreme conditions, life always found a way to adapt and harness the planet's energy, no matter what form it took. On land, animals also sought new ways to survive. One of the most successful strategies was burrowing. Numerous reptiles and small synapsids mastered this art to escape the scorching heat, using underground tunnels as natural air conditioners. These burrows were more than just a refuge from predators. They helped conserve precious moisture in an arid world. Fossilized remains from those times reveal entire underground cities with complex networks of passages, living chambers, and nests, indicating advanced social behavior. Some animals even shared their burrows with other species, forming small communities where survival depended on cooperation. A revolution was also taking place in reproduction methods. The development of the amniotic egg was one of the greatest inventions in the history of life on Earth. By encasing the embryo in a strong protective shell with a reserve of nutrients, animals broke the ancient shackles that bound them to water. This opened the way for them to explore deeper into the continents, to deserts, forests, and mountains. This innovation, which had arisen even earlier, became widespread during the Permian period, allowing reptiles and synapsids to conquer new worlds. Reproductive strategies became increasingly sophisticated. Some species laid their eggs in deep, hidden nests, while others carried them inside their bodies until hatching. And although parental care was still rare, its first tentative manifestations were already beginning to emerge, a crucial evolutionary step that would shape the future of many species for millions of years to come. Plants didn't lag behind, developing their own ingenious strategies. In regions where wildfires were common, trees developed thick, fire-resistant bark, and some developed cones that opened to release seeds only when exposed to intense heat. These seeds fell into ash-rich soil, getting a head start thanks to the nutrients released by the fire. In arid zones, plants grew incredibly long roots to reach groundwater, or reduced their leaf area to reduce evaporation. Some even adopted a guerrilla lifestyle, awakening after rare rains for a short but profuse flowering, then returning to dormancy during periods of drought. These adaptations gave rise to entirely new landscapes: savannas with sparse trees, vast shrub thickets, and sparse forests that covered vast swathes of Pangea. The relationships between plants and animals also became more complex. Herbivores became more selective, preferring specific plant species, which, in turn, influenced the vegetation of entire regions. The global system of life on the planet was reorganizing itself, becoming increasingly resilient. Ecosystems were now less dependent on a single species or stable conditions. When drought struck or fire raged, life learned to quickly recover as soon as the threat passed. The fittest survived. Those who could endure adversity, accumulate energy, migrate long distances, or demonstrate reproductive flexibility. Even microscopic organisms played an indispensable role in this. Soil bacteria and fungi tirelessly decomposed organic matter, ensuring nutrient cycling and stabilizing the soil itself. Without their invisible work, ecosystem restoration would have been simply impossible. The Earth's biosphere acted as a unified, self-regulating mechanism, where every species, even the tiniest, contributed to overall stability. And, of course, predation remained the primary driver of evolution. It was a never-ending arms race. As herbivores grew larger and armored, predators responded by developing more powerful jaws, sharper claws, and faster legs. This deadly game between hunter and prey drove the emergence of ever-new species. On the open plains, large synapsids and agile reptiles reigned supreme, while in rivers and swamps, predatory amphibians dominated. Fossils from this era bear witness to this race. We find specialized teeth designed for crushing bone or cutting flesh, and bones adapted to specific lifestyles. All these changes indicate that ecosystems were becoming increasingly complex, capable of supporting truly large animals and complex food chains. Even in the most difficult times, evolution never stopped for a moment. Imagine our planet, but completely unrecognizable. This is not the familiar blue sphere with the outlines of familiar continents. Before us is a living, breathing mosaic of scattered islands, young mountain ranges, and endless, shallow seas. What we today call the Earth's crust was already in constant, albeit leisurely, motion in those distant times. It was caught and carried by powerful currents of the molten mantle, seething deep within. To understand this picture, imagine a giant cauldron of incredibly thick liquid slowly simmering over an invisible fire. Hot material from the depths rises, gives off heat, cools, and sinks back down, causing the solid plates on the surface to swirl in an endless, majestic dance. Over hundreds of millions of years, this slow motion has created and destroyed oceans, shifted continents, pushed them together, and torn them apart again. From a human perspective, this movement is completely imperceptible, but on the scale of geological time, it has the potential to change the face of the entire planet. When we speak of the birth of Pangea, we are not talking about a single event, but rather a long and grand process of reuniting disparate lands. After all, continents had already merged in the past, forming supercontinents with mythical names that scientists have given them in modern times: Rodinia, Nuna, and others. Pangea was the last of these titans, the last great supercontinent that existed before the world took on its modern shape. Its formation began somewhere between the late Carboniferous and early Permian periods, about 300 million years ago. Let's travel back to that era. Two colossal continents, Laurasia to the north and Gondwana to the south, began their inexorable dance of convergence. As they crept toward each other, the oceans that had separated them for millions of years compressed and eventually disappeared. And at the site of their collision, where the edges of tectonic plates collided, The Earth's crust crumpled like paper, lifting new mountain ranges skyward. In their youth, they would have rivaled the modern Himalayas in height, and so, in the midst of this tectonic storm, Pangea was born, a colossal continent stretching almost from pole to pole. It's hard to even imagine its true size. If you were at its very center, you'd have to travel for weeks, even months, to even see the ocean shore. The interior of this supercontinent was so vast that the moist winds from the coast simply couldn't reach it. This meant a world of extremes, long, debilitating droughts, scorching heat by day, and freezing cold at night. Endless deserts stretched beyond the horizon, far beyond any modern-day Sahara. The air itself was different. The balance of gases in the atmosphere was different from what we breathe today. Oxygen levels rose and fell, and winds swept across the endless plains. The planet's climate changed not from year to year, but over entire geological epochs. Sometimes the world succumbed to heat and drought, sometimes it was frozen solid, but it always remained vibrant, full of wondrous creatures. It was one of the most dramatic transitions in the history of life on Earth. The Carboniferous period had passed, an era of vast swamps and dense, humid forests, home to giant ferns and giant insects thriving in the oxygen-rich atmosphere. As Pangea finally formed, much of this lush vegetation began to disappear. As the climate dried, the swamp forests retreated, giving way to more resilient plants, conifers, seed ferns, and other species capable of surviving in the new arid conditions. This change in scenery set off a chain reaction in the evolution of all life on land. Insects were forced to adapt. Reptiles became increasingly diverse, capturing new ecological niches. And it was then that the first true ancestors of mammals, the synapsids, began to appear. Their warm-blooded bodies gave them an advantage in this world of sharp temperature fluctuations. The surface of Pangea itself was a patchwork of vastly different worlds. Forests and river systems stretched along the coasts, providing shelter for amphibians, reptiles, and early synapsids. Further inland, dusty plains stretched, where survival was a harsh daily challenge. And closer to the poles, the climate could be downright unpredictable. Ice caps advanced and retreated, obeying the slow cycles of the planet's rotation. In every corner of this gigantic world, life pulsed to its own rhythm, balancing on the brink of survival and adaptation, reflecting the great tectonic processes that shape the planet itself. The oceans surrounding Pangea were no less impressive than the land itself. To the west and north lay Panthalassa, a global ocean that occupied almost the entire remaining hemisphere. To the east, wedged between the converging continents, lay the Tethys Sea, smaller in size but still vast. And these waters were teeming with life. Ammonites floated within their depths, coiled in their perfect spiral shells. Trilobites, whose era was already drawing to a close, still clung to existence on the seafloor. And early sharks and bony fish were already patrolling the depths in search of prey. Coral reefs towered in the warm shallows, though not built by the species we know today. Ancient corals, such as rugosa and tabulate corals, created their own underwater cities long before their modern descendants emerged. Once, in this distant past, our world was one. Every modern coastline is a scar, a reminder that the continents were once connected. Scientists studying the history of Pangea are finding clues to this mystery scattered across the globe. Fossils of the same ancient species are found on continents that are now separated by thousands of kilometers of ocean. Rock layers match perfectly if you mentally connect South America and Africa. The very outlines of the continents, when viewed on a map, resemble pieces of a giant puzzle. The first person to dare to suggest that all this evidence pointed to something incredible, continental drift, was the German meteorologist Alfred Wegener. At the beginning of the 20th century, his idea was met with hostility. The scientific community considered it too bizarre, almost fantastical. But in the following decades, evidence continued to accumulate. The study of ancient Earth magnetism, the mapping of the seafloor, and, finally, the direct observation of tectonic plate movement, all this confirmed Wegener's brilliant insight. Tectonic plates became the foundation of modern geology, and his vision became one of the cornerstones of this science. The formation of Pangea was not a single event, but spanned tens of millions of years. The northern continent, Laurasia, emerged when what would become North America and Eurasia merged. To the south, the gigantic Gondwana united the lands we now know as South America, Africa, Antarctica, India, and Australia. And when these two supercontinents collided, a single world was born. Mountains rose along the lines of this monumental collision, particularly in what is now the eastern United States, northern Europe, and parts of Africa. These were the young Appalachians, the Urals, and other mountain ranges, silent witnesses to the terrifying force of the collision of entire continents. How strange it is to realize that what we see today as separate land masses was once a single surface. The ocean floor turned out to be not a flat and lifeless desert, as previously thought, but was pierced by colossal mountain ranges, mid-ocean ridges stretching for tens of thousands of kilometers. Along these ridges, molten rock rose from the Earth's interior, cooled, and formed a new seafloor. As new crust was formed, it pushed older layers apart, and at the opposite ends of the oceans, in deep-sea trenches, the old crust sank back into the mantle. It turned out that Earth constantly reworks its own surface, creating and absorbing crust in a never-ending cycle. This process, known as seafloor spreading, became the missing link in Wegener's theory, the mechanism that moves the continents. They weren't floating on their own, they were merely passengers, carried by enormous plates floating on the surface of the viscous mantle. Our planet wasn't static, it had its own dynamic, turbulent life. This movement was so slow that we would never have noticed it, but its power was capable of changing the face of the entire world. By the 1960s, the theory of plate tectonics had emerged, uniting geology, seismology, and oceanography into a unified, coherent picture of the world. The mystery of drifting continents was finally solved. To understand this, imagine the Earth not as a solid sphere, but as a living system. The crust we stand on is a thin shell compared to the molten rock beneath. Where plates collide, incredible processes occur. Some create new mountains, while others are absorbed into the mantle. Along mid-ocean ridges, magma rises, releasing energy in the form of earthquakes and cooling to form new crust. And along deep-sea trenches, old crust sinks back into the interior. The continents, being thicker and lighter, float like giant rafts on this sea of molten rock. Over time, they converge or move apart, collide and separate, creating mountains and new oceans. The patterns of these movements form cycles spanning hundreds of millions of years. One such cycle is known as the supercontinent cycle. Throughout Earth's geological history, massive continents have repeatedly coalesced and then broken apart. Pangea was only the latest in this series, but far from the first. Before it, other supercontinents formed and disintegrated under the influence of inexorable forces hidden deep within our planet. Evolution never paused. It didn't start from scratch. No, it masterfully adjusted its rhythm, honing existing life forms to the ever-changing rules of the game. Imagine this world. The arrangement of all life on the gigantic continent of Pangea was dictated by two great forces, geography and climate. The hot tropical zones bordering the ancient Tethys Ocean were perpetually scorched and drenched by seasonal rains. It was a veritable paradise for life, where dense, lush jungles teemed with an incredible diversity of creatures. However, move from the equator to the poles, and the landscape changed beyond recognition. The world became colder, harsher, more hostile. Lush forests gradually gave way to endless open plains, and then completely gave way to landscapes reminiscent of modern tundra. Here, at the edge of the world, only the most resilient and undemanding plants clung to the parched, thin soil. And then, for many, the Great Migration became the only chance for survival. Migration became a fundamental survival strategy, allowing animals to follow favorable weather, like nomads chasing the changing seasons. Ancient fossils provide irrefutable evidence of this phenomenon. Paleontologists find evidence of entire animal species traveling thousands of kilometers. Their remains are discovered in regions vastly distant from their ancestral lands. On the scale of geological time, these wanderings were certainly slow, but it was they that wove together the ecosystems of the entire supercontinent. Life's flexibility also manifested itself on an invisible chemical level. Ancient organisms learned to control their metabolism, adapting it to extreme temperature fluctuations. Some reptiles, for example, could virtually halt their vital processes during severe droughts, entering a deep hibernation to conserve precious energy. Other creatures relied on behavior. They sought sheltering shade during the midday heat, postponed hunting and feeding to the cool hours of the night, or dug deep burrows to escape the merciless sun. This physiological plasticity allowed them to survive in a world that was changing far faster than their bodies could evolve. Behavior became the bridge between biology and harsh reality, allowing life to endure under conditions of endless stress. Millions of years later, this mosaic of life took on a clear outline. Recognizable natural zones, or biomes, formed: deserts, forests, river valleys, and coastal plains. Each acquired its own unique ecosystem, its own inimitable web of predators and prey. The inland deserts of Pangea remained vast, sun-baked expanses where only the most resilient reptiles and thorny, hardy plants reigned supreme. Coastal zones and river systems, by contrast, supported a far greater diversity of life. During dry periods, they became the last oases, true refuges for those seeking refuge from thirst. The delicate balance between these regions constantly shifted under the influence of climate, but the overall structure of the world remained unchanged. Life, like water, found a way to seep into any available niche, no matter how tiny. But in this world, seemingly obsessed with challenging all life, every adaptation, every evolutionary trick had its price. The energy an organism expended on protecting itself from heat or cold was no longer available for growth or reproduction. And different species solved this dilemma in their own ways. Some opted for quantity, producing huge numbers of offspring in the hope that at least one of the hundreds or thousands would survive. Others chose a different path: quality. They bore only a few young, but invested maximum care and resources in each one. Over time, these strategies determined which dynasties would flourish and which would vanish forever from the pages of history. Thus, a biosphere was formed, woven from constraints and possibilities, a system designed to survive, but not necessarily to thrive. The resilience of this Permian world was astonishing, but it was not eternal. Deep beneath this seemingly stable surface, a geological clockwork ticked. The same forces that had once woven Pangea together continued their work. Volcanic activity continued unabated, slowly but surely saturating the atmosphere with carbon dioxide and influencing global temperatures. For now, planetary systems, atmosphere, ocean, vegetation, coped with these changes, maintaining a delicate equilibrium. However, this balance was like a taut string. The very adaptations that had helped life survive, flexibility, drought tolerance, efficient respiration, unwittingly prepared it for a future where trials would be even greater. But for now, the great experiment continued. The forest stood firm, the desert breathed scorching air, the oceans carried their currents, and life went on as usual, accepting new challenges with the same endless patience. The apocalypse didn't arrive with a deafening roar. It crept up quietly, almost on tiptoe, so unnoticed that not a single living creature on the planet would have suspected trouble. On the surface, everything was as before. The forests still rustled in gusts of dry wind. The seas rolled lazily, and the gigantic continent continued its almost invisible drift beneath the same pale, faded sky. But this was only the calm before the storm. Deep within the planet's bowels, true chaos was brewing. The great balance of the world had been disrupted. The forces that had once created Pangea were now preparing to destroy it. Beneath its colossal mass, an unimaginable amount of heat had accumulated, a gigantic heat bomb, desperately seeking a way to the surface. In the distant northern reaches of the supercontinent, in the territory of future Siberia, where volcanic activity had been quietly smoldering for a long time, the Earth's pulse began to quicken. Temperatures began to rise, and the first ominous signs of impending catastrophe appeared in the air and water. The atmosphere, already warm and dry, began rapidly accumulating carbon dioxide. At first, the difference was negligible, almost imperceptible, but the effects accumulated. Global temperatures began to rise, disrupting normal precipitation patterns and pushing fragile ecosystems to the point of no return. Deserts began to advance, devouring regions where forests once flourished and rivers flowed. Coastal zones, which for centuries had served as the last refuge for life, began to suffer from unpredictable seasons and prolonged, debilitating droughts. Monsoons, which brought life-giving moisture, became increasingly rare and chaotic. The climate, which was already extreme, has now become a wild swing. Deep underground in the mantle, slowly heating up under the weight of Pangea, an explosion was brewing. The continental crust was so thick that it acted like a lid on a boiling cauldron, preventing the energy from escaping. When the pressure reached a critical point, the mantle began to melt at its hottest points. Molten magma rushed upward, forcing its way through cracks and weak spots in the crust. This was more than just a volcanic eruption. It was an entire geological era of fire, stretching for millions of years. In what is now Siberia, the Earth literally burst at the seams. Streams of molten rock gushed from gigantic fissures, spreading across the surface for hundreds of kilometers, covering everything with layers of lava several meters thick. These were not the familiar cone volcanoes we are accustomed to, but veritable lava floods. Rivers of fire flooded vast territories, leaving behind only scorched, dark, and completely lifeless plateaus. Each fiery geyser spewed monstrous quantities of gases into the sky. Carbon dioxide, methane, sulfur dioxide, and water vapor. This toxic mixture altered the chemical composition of the atmosphere on a global scale. Carbon dioxide enveloped the planet like a blanket, trapping heat and accelerating the already ongoing warming. Sulfur dioxide, in turn, created an aerosol curtain in the upper atmosphere that reflected sunlight. This led to brief periods of cooling, followed by even sharper and more intense heating. The planet swung from heat to cold. The atmosphere filled with dust and haze, blocking ever-decreasing amounts of sunlight. The seasons descended into chaos. The world's oceans, which for centuries had served as a giant sponge soaking up excess carbon dioxide, began to suffocate. They were overflowing. Absorbing more and more CO2, the water turned into a weak solution of carbonic acid. Ocean acidification began. This was a death sentence for numerous marine organisms whose shells and carapaces were composed of calcium carbonate. The acid literally ate away their skeletons. Corals, brachiopods, and billions of microscopic planktonic creatures found themselves on the brink of extinction. Their growth slowed, their protective shells thinned. The fragile ocean chemistry that had supported entire underwater civilizations was crumbling before our eyes. At the same time, atmospheric heating increased the temperature of surface waters, and warm water holds far less oxygen. The powerful ocean currents that carried oxygen from the surface to the depths weakened. Dead, anoxic zones began to expand rapidly. These zones became a feast for anaerobic bacteria, microscopic creatures that didn't require oxygen. Their byproduct was hydrogen sulfide, a deadly poisonous gas. As their populations grew, the gas accumulated in the deep waters. While the oceans mixed, it remained trapped at the bottom. But now, with the circulation weakening, the boundary between the oxic and anoxic layers rose to the very surface. Then, hydrogen sulfide began to escape into the atmosphere, poisoning all life on land and in the sea. the suffocating smell of rotting sulfur carried on coastal winds, an ominous whisper that the planet's equilibrium had finally collapsed. The toxic breath of the Siberian eruptions knew no bounds. Gases and ash particles were carried by winds across the globe, reaching both hemispheres. Layers of grey ash covered continents, leaving ominous marks in the geological record. Acid rain poured from the skies, scorching the last nutrients from the soil and washing them into the poisoned ocean. Rivers, once full-flowing arteries of life, turned into murky, toxic torrents. Imagine the rains, now caustic and acidic, washing away the last nutrients from the lifeless land, carrying a toxic cocktail of minerals and toxins straight into the sea. The planet, recently cloaked in a vibrant green carpet of forests and meadows, began to rapidly become bald. Where once mighty tree roots held the soil in place, nothing now prevented the wind and water from sweeping it away, setting off a terrifying cycle of total devastation. The skies overhead darkened. The air turned into a thick suspension of ash and dust, which, like dirty glass, blocked the life-giving rays of the sun from reaching the surface while trapping the stifling heat below. On land, a true tragedy was unfolding for the entire plant world. Even the few forests that had miraculously withstood the droughts and firestorms now began to slowly die. They retreated, unable to withstand the onslaught of new hostile conditions. Rising temperatures and chaotic, unpredictable rainfalls confused the ancient plants that had become accustomed over millions of years to a strict seasonal schedule. Fires became commonplace, flaring up with increasing frequency and ferocity. They were fueled by vegetation parched like gunpowder and endless thunderstorms born in clouds charged with volcanic ash. Once thriving and interconnected ecosystems fell apart, becoming pitiful, isolated pockets of surviving flora. The mighty conifers and spreading shrubs that dominated these landscapes for centuries now find themselves on the brink of extinction. Million years after million years, the world sank into decay. The great red deserts of the supercontinent Pangea spread like a cancer, mercilessly devouring the last fertile lands. The planet's surface became a lifeless patchwork of dust, rock, and sand. Rivers, once the arteries of life, dried up, leaving behind only dead channels clogged with silt instead of life-giving moisture. The first to bear the brunt were those who fed on plants. Herbivores faced horrific starvation, and as their herds dwindled, the predators that hunted them also suffered the same fate. Long before the Siberian volcanoes spewed their hellish fire, many giant synapsids, our distant relatives, had already vanished from the face of the earth. Their bones ceased to appear in the fossil record, suggesting a slow but inexorable decline. Smaller creatures, requiring fewer resources to survive, fared somewhat better, but even they were devastated by the climate chaos. Reproductive cycles were disrupted, and ancient migration routes no longer aligned with the seasons. Egg clutches were destined to mate. They simply dried out in the scorching sun, and burrows, once a safe haven, turned into death traps. Then, without warning, catastrophic rainstorms could descend, washing away everything in their path. Entire food chains were torn and disintegrated. Every day the situation became worse, and the world around us became more and more unpredictable. Meanwhile, a similarly horrific catastrophe was unfolding in the oceans. The seafloor became a vast cemetery. Thick layers of black shale formed in dead, anoxic zones, evidence that organic remains accumulated far faster than they could decompose. Coral reefs, those underwater megacities of life, crumbled and died, their limestone skeletons simply dissolving in the increasingly acidic waters. Trilobites, incredible creatures that had survived several mass extinctions over hundreds of millions of years, failed this time and vanished forever. Ammonite and brachiopod populations collapsed, and the overall diversity of marine life declined to catastrophic levels. Once vibrant, shallow seas became bleak, muddy deserts. Even plankton, the microscopic base of the entire marine food chain, suffered colossal losses. This blow to the very foundation of life disrupted the entire chain, from the tiniest organisms to the largest marine predators. The oceans grew ever warmer. And even more terrifying, here, at the bottom, another deadly mechanism was triggered. Under the water, gigantic reserves of methane hydrate, essentially frozen flammable gas, slumbered. Now, as the depths warmed, these ice cells began to melt, releasing colossal volumes of methane into the atmosphere. Methane is a greenhouse gas, many times more potent than carbon dioxide. Its release was the final nail in the coffin of a dying world, confirming that the Siberian eruptions had already set in motion an irreversible process. Temperatures on Earth continued to climb, and this vicious cycle gained terrifying speed. The hotter it got, the more methane emerged from the ocean depths, and the hotter the planet became. Once started, this cycle was virtually impossible to stop. The combined impact of volcanic gases, ocean acidification, and the runaway greenhouse effect distorted the planet's carbon cycle beyond recognition. The delicate balance between how much carbon is emitted into the atmosphere and how much is absorbed was completely destroyed. Land vegetation could no longer inhale enough carbon dioxide to offset its emissions. Oceans, already oversaturated with carbon, lost their ability to absorb it. The result was a domino effect, turning the atmosphere into an increasingly hostile environment. The planet's average temperature is believed to have jumped by 5 to 10 degrees Celsius. This was more than enough to completely reshape all ecosystems. The polar ice caps melted without a trace, sea levels changed dramatically, and familiar weather patterns shifted. The distinctions between the equator and the poles blurred as extreme weather conditions became the norm across the planet. The fossil record of that dark period is a story of total devastation. In some places, up to 90% of all species disappeared from the seafloor, and on land, around 2/3 of all vertebrate families went extinct. Although the extinction process itself spanned millions of years, in geological terms, it occurred virtually overnight. It was the greatest catastrophe, the most brutal mass extinction the Earth has ever known, and it was caused not by a single catastrophe, but by a deadly chain reaction of interconnected impacts. The planet's internal heat, unleashed through Siberian volcanoes, triggered a cascade of atmospheric and oceanic changes that turned the world upside down. And yet, despite this apocalypse, some life forms managed to cling to existence. Certain species of burrowing reptiles and amphibians found refuge underground, where temperatures remained more or less stable. In the ocean, several of the hardiest species of ammonites and microscopic plankton managed to survive in small oases, zones where oxygen-rich water still flowed. Their survival was not just dumb luck, but the result of their incredible ability to adapt to new, nightmarish conditions. Adaptation proved key. Areas of the ocean where deep currents brought oxygen to the surface became the last refuges, and simultaneously the cradles of new life. The species that inhabited these areas became the ancestors of future ecosystems, beginning the long journey to recovery. However, most of the world was plunged into a ringing silence. The atmosphere at that time was strange, heavy, and oppressive. Volcanic gases shrouded the sky in a dense haze, giving the sunlight a sickly, reddish tint. Ash and dust particles hung in the air for years after each major eruption, scattering light and causing brief periods of cooling before the greenhouse effect took over again. These swings, from heat to cold and back again, dealt another blow to surviving ecosystems, preventing them from recovering. Plants that tried to push through the ashes after the fires were immediately killed by sudden frosts, or, conversely, incinerated by a new heat wave. But life is a stubborn force. Following the plants, insects returned to the scorched earth. Their diversity, of course, was only a shadow of its former splendor, but it was a first step. Beetles, flies, and the primitive ancestors of modern grasshoppers reclaimed the world. They became the unnoticed but vital engineers of a new ecosystem. By recycling dead organic matter, they accelerated the regeneration of the soil. The land, once lifeless and barren, was once again filled with nutrients, giving new growth a chance. The connections between plants and insects, severed during the catastrophe, began to slowly rebuild. Each new generation made the world a little more stable, preparing the ground for the slow return of more complex life forms. In the oceans, the first signs of rebirth came from plankton, which once again became the foundation of the food chain. Its rapid reproduction provided food for small invertebrates and fish. Coral reefs, completely destroyed during the extinction, began to rebuild in shallow, oxygen-rich waters. These were different reefs, created by new species adapted to a warmer and more unstable environment. Sea lilies, mollusks, and ammonites began to branch out again on the evolutionary tree, occupying vacant ecological niches. The oceans, until recently dark, dead, and silent, once again filled with movement and life. Level by level, the food chain was restored, returning to its pristine balance. The restoration of marine life, in turn, helped stabilize the planet's climate. Microscopic plankton, for example, greedily absorbed carbon dioxide from the atmosphere and, after dying, carried it to the ocean floor, preserving it for millennia. The carbon cycle gradually returned to its natural rhythm, restoring the balance between air, land, and sea. Planetary systems, though still incredibly fragile, began the process of self-healing. Each new generation of living beings made a tiny contribution to the restoration of the biosphere, making it more resilient. And on land, where firestorms had recently raged, the first forests of a new era were sprouting. Conifers and seed ferns colonized the coastlines and uplands. Their roots dug into the new soil, anchoring it. Their crowns provided sheltering shade, cooling the surface and retaining precious moisture. Streams, once choked with ash, cleared and flowed through the valleys again, gradually preparing them for the arrival of more complex life. Amphibians returned to these pools. Their croaks and trills echoed in the moist air. Myriads of insects filled the space between water and land, and these, in turn, began to be preyed upon by small, nimble reptiles. Food chains, once shattered, began to reweave, linking species in an eternal cycle of energy and the struggle for survival. Atmospheric oxygen levels, which had fallen catastrophically during the extinction, slowly but surely began to rise. Imagine a world slowly recovering from a global catastrophe. With each new leaf breaking through the parched soil, with each colony of plankton thriving in warm waters, the planet's atmosphere begins to change. Oxygen levels, once critically low, begin their long climb back up. The air, recently turbid and acrid, becomes clearer. The thick veil that had obscured the sun for centuries finally dissipates, and the sky regains its pristine deep blue. The ocean surface, previously dull and lifeless, begins to sparkle with sunlight once again. The planet, having survived the fiery inferno, has cooled enough for the climate to become more predictable. Weather systems are stabilizing. In some regions, rainfall is becoming a regular occurrence, feeding dry riverbeds and filling ancient lake basins. Where once there were only endless deserts covered in a layer of blood-red dust, the first green oases are now appearing. These islands of life grow with each passing century, reclaiming more and more territory from the dead land. The land, scarred by volcanic eruptions, is once again finding the pulse of life. This time, evolution isn't just progressing, it's racing forward at breakneck speed. After the Great Extinction, an incredible number of empty spaces, vacant niches, emerged in nature. Natural selection, that great sculptor of life, was given carte blanche to experiment even bolder. New life forms continually emerge, each proving slightly better, adapted to the changing conditions than its predecessors. The reptiles that survived this crucible begin to divide into numerous groups, destined to become the sole masters of the Mesozoic era. Amphibians, whose numbers have dwindled significantly, still cling to life in swamps and shallow waters, their familiar world. And in the ocean depths, a new dynasty is born. The first ancestors of giant sea lizards appear on the scene. Their bodies, still clumsy, are already beginning to acquire streamlined shapes, ideal for hunting in the aquatic environment. All this evolutionary trial and error will lay the foundation for all life for the next 250 million years. It is here, in this slow but steady rebirth, that future ecosystems are forged, where dinosaurs, the first mammals, and the life of modern oceans will emerge. Even geological forces that until recently brought only destruction are now working to restore. Relentless erosion is wearing down giant volcanic plateaus, and water currents are carrying precious minerals into the ocean. These nutrients become a veritable feast for marine microorganisms. Plankton growth accelerates, triggering a chain reaction of reviving marine food chains. The weathering of basaltic rocks continues, but now it plays a different role. It actively absorbs carbon dioxide from the atmosphere, helping the planet cool even more rapidly. The great cycles of carbon, oxygen, and water that determine life on Earth are being restored. Chaos is gradually giving way to order. The planet is regaining harmony. The traces of this great tragedy are forever etched in stone. Geologists around the world are finding a distinct boundary in the rocks, dark layers of volcanic ash and black shale that, like a bold line, separate the old world from the new. In these layers, the fossils of countless ancient species simply vanish, and above them appear the remains of entirely different creatures, their successors. In some places, this transition is abrupt and sudden, like a cliff. In others, it is more gradual. This dividing line became the geological boundary between the Permian and Triassic periods, the moment when Earth began its great healing. The planet's rock record preserves both evidence of total destruction and the first signs of a coming rebirth. For millions of years, the planet's climate remained highly unstable, but the overall trend was positive. Temperatures were still high, but no longer rising uncontrollably as they had at the height of the catastrophe. Precipitation increased, and deserts slowly retreated under the onslaught of vegetation. Greenery gradually conquered new territories, and the soil became deeper and more fertile thanks to the decay of organic matter. Rivers carved new channels, intertwining into a complex network that carried sediment from the mountains to the seas, forming vast deltas and coastal plains. These new landscapes became a cradle of biodiversity, where life flourished in forms the world had never seen before. The Earth's surface, once resembling a parched Mars, became a living mosaic of thousands of ecosystems. The slow cooling of the atmosphere reintroduced seasons to the planet. Regions previously dominated by perpetual heat and drought began to experience predictable cycles. Wet seasons followed dry ones, and periods of heat gave way to relative coolness. And life immediately responded to these rhythms. Organisms began to synchronize their life cycles with the changing conditions. Forests grew vigorously during warm and humid periods, shedding their leaves during droughts. Animals learned to migrate with the rains or hibernate to survive lean times. The great natural cycles, disrupted by the volcanic winter, returned, restoring their lost balance. In this renewed world, the boundaries between old and new dynasties of life became blurred. Many evolutionary lines that survived the extinction event gave rise to astonishing and sometimes bizarre descendants. Synapsids, our distant ancestors, gave rise to new species with more sophisticated metabolisms and specialized teeth. Reptiles, however, took a different path, evolving into the ancestors of crocodiles, lizards, and, of course, the future kings of the planet. The dinosaurs. Ammonites reappeared in the oceans, and new coral species began the painstaking work of restoring reefs. The planet's biosphere was not yet as complex and diverse as before the catastrophe, but it was full of youthful, unbridled energy. Evolution raced forward at full speed, as there was virtually no competition. All that was needed was to fill the void. However, the recovery process was uneven across the planet. Some regions remained barren for much longer than others, particularly those at the epicenter of volcanic activity. While the coastal zones of the ancient Tethys Sea revived relatively quickly due to their proximity to water, Others, covered in kilometers-thick layers of basalt, such as the Siberian traps, remained dead zones for a long time. On these isolated worlds, evolution followed its own independent paths, which eventually led to an explosion of species diversity. What began as a desperate struggle for survival gradually transformed into an era of great discovery and innovation. Life didn't simply adapt, it actively explored the new opportunities presented by the changing world. With the onset of the Triassic period, planetary systems finally achieved long-awaited stability. The carbon cycle was balanced, ocean currents circulated freely across the globe, and the composition of the atmosphere stabilized. Temperatures dropped to comfortable levels, and dense forests once again covered most of the land. Rivers flowed full-flowing year-round, and the seas were saturated with oxygen and nutrients. The planet created all the conditions for a new flourishing of life. Having survived the most terrible crisis in its history, the world changed beyond recognition. But it endured. Life, forged in this ordeal, will never be the same. It will forever preserve in its genetic memory the legacy of resilience that has defined it for billions of years. The memory of the catastrophe lives on in the very processes that govern the planet. The geological cycles that regulate the Earth's climate and chemical composition have changed. The balance between volcanic gas emissions and their absorption has become more subtle, more precise. Surviving organisms have strengthened the biological feedback mechanisms that stabilize the climate. It could be said that the Earth has been through fire and learned to more effectively maintain its own equilibrium. This new world, rising from the ashes, laid the foundation for the Mesozoic era, an era that would witness the emergence of giant dinosaurs, the rise of sea monsters, and, ultimately, the evolution of our direct ancestors, the mammals. Every living thing that emerged afterward owes its existence to those humble heroes who survived the Great Dying. The microbes that first colonized the cooling lava, the plants that stubbornly took root in the ash, and the small animals that found refuge in deep burrows underground. Their titanic labor allowed the history of life to continue. The past wasn't erased, it became the foundation for the future. Layers of basalt, rusty soils, and fossils of extinct species will forever remain in the geological record as a reminder of what the Earth has endured. Each new generation of living beings literally built their lives on the ruins of the old world, turning them into the foundation for the future. Yes, the Earth once burned, suffocated, and was one step away from complete sterility. But this didn't stop it. From the first slimy films of microbes on solidified lava, to the return of endless forests and the slow oxygenation of the oceans, the planet has repeatedly demonstrated its incredible thirst for life. This renewal was no miracle. It was a long series of tiny changes, each one obeying the three great laws of nature: adaptation, persistence, and time. These were the laws that drove the planet forward. And then, after the firestorm, a deafening silence descended, gradually replaced by the sounds of new life. The world was once again filled with color and sound. The rustling of leaves in young forests, the murmur of water in full-flowing rivers, and the soft buzz of the first insects. The air was permeated with life. Sunlight, now bright and pure, pierced the atmosphere, as if dispelling the last shadows of the past. The sky became brighter, the air cooler. The world, having endured the most severe trial, had changed, but it had survived. The Earth, once reduced to ashes, was once green. The oceans, once lifeless and dark, shimmered once again with myriads of living lights. We had entered a new era. Deep scars remained on the face of the planet, but with them came a calm certainty that life is an integral part of this world. The world, rising from ruins, was reassembled from fragments, but its foundations remained unshakable. The vast supercontinent of Pangea still stretched from pole to pole, determining global winds, currents, and migration routes. And although its forests were still young, and its ecosystems were only just forming, this world continued to live, preserving in its depths the memory of an ancient union of rock and life that cannot be broken. The traces of this titanic world, this ancient supercontinent, are still carved into the very body of our planet. We see them in the outlines of modern continents, like pieces of a gigantic puzzle. We find them in ancient rocks that serve as silent witnesses to its former grandeur, and even in the very composition of the air, forever changed by its birth. Even millions of years after the Permian catastrophe, the colossal Pangea still reigned supreme over the planet. Its immense shores were lapped by the waters of the great Panthalassa Ocean on one side and the warm Tethys Sea on the other. And in the very heart of this gigantic landmass, a harsh, arid climate reigned, a legacy of the same slow air circulation that created lifeless deserts in bygone eras. The volcanic fires that once tore the Earth's crust apart had long since subsided, but the planet's depths were far from calm. Beneath the continental plate, the molten mantle still churned. Its powerful convection currents, like invisible titans, continued to push and pull the tectonic plates from within. The very forces that had once welded this supercontinent together were now plotting its inevitable destruction. However, this grandiose divorce would take time. Tens of millions of years passed before the first deep scars began to appear on Pangea's surface. These invisible faults, hidden within the Earth's crust, slowly, millimeter by millimeter, spread apart in the deathly silence of the depths, and on the surface, where these deep processes raged, life continued its great transformation. Mighty rivers, whose channels were once buried under layers of volcanic ash and sedimentary rock, now cut a path for themselves once again, gnawing into the rocky flesh and revealing new pages of geological history with each passing century. The majestic mountains born from the titanic collisions of continents during the formation of Pangea began their long journey to oblivion. Their jagged peaks, once clawing at the sky, were slowly smoothed by the relentless onslaught of wind and rain. Minerals and nutrients leached from these dying mountains were carried by rivers into the oceans. There, they became food for plankton, triggering a chain reaction of marine life revival and the restoration of the entire ecosystem. Life continued to evolve in an eternal dance with geology. Solid Earth and the living biosphere were inextricably linked into a single ever-changing system. As ecosystems recovered, the planet's very appearance took on new features. Vast forests began their triumphant march across temperate regions, creating landscapes of incredible diversity. Broad green belts, defined only by rainfall, stretched across the supercontinent. Swamps and lakes returned to the land, creating ideal conditions for amphibians and the first primitive reptiles to thrive. Ancient forests filled with the buzz of myriads of insects, pollinating plants and serving as indispensable cleaners, processing tons of organic matter. The endless plains teemed with life. Small reptiles and synapsids, our distant ancestors, hunted, dug burrows, and foraged for food. Their entire lives were governed by the ancient rhythm of day and night, heat and cold. The planet found a new, fragile balance, which became a cradle for the emergence of increasingly complex and amazing life forms. The ocean, too, was undergoing a period of great change. The warm, shallow waters of the Tethys Sea became a veritable incubator of evolution. Coral reefs, devastated by the extinction, flourished again, spawning hundreds of new species of corals and sponges. Fish experienced an explosion of diversity, rapidly occupying ecological niches that had been vacant since the catastrophe. Ammonites hovered in the water column, their spiraling shells serving as living chronometers, measuring the slow passage of geological time in the sediments. Each new generation of these creatures left behind calcium, carbon, and a particle of life on the ocean floor, bit by bit, restoring the former splendor of the marine world. Stagnant, dead depths were once again in motion. Ocean currents once again circulated freely, bringing oxygen to the darkest abysses and allowing complex organisms to colonize even these inhospitable worlds. The ocean, which had been literally suffocating, was now breathing deeply. Pangea was still a single entity, but its colossal size dictated its own laws for everything around it. Winds distributed heat extremely unevenly across its surface, generating powerful monsoons on the eastern coasts and drying dry winds on the western plains. But the harshest conditions reigned in the heart of the continent. The interior was a world of extremes. Scorching heat during the day gave way to icy cold at night, and rain could go for years. The coastal regions, influenced by the ocean, enjoyed a much milder and more stable climate, moderated by sea breezes. These contrasts became the primary drivers of evolution on the supercontinent. Species living along the coasts adapted to a humid and predictable environment, while those living in the central deserts had to develop incredible survival mechanisms in harsh conditions. Some learned to live by the rhythm of seasonal rains, while others evolved to withstand relentless heat and drought. This incredible diversity of landscapes and climates laid the foundation for a future explosion of life. The memory of the supercontinent was also preserved in the way the Earth's crust responded to its colossal weight. Beneath Pangea, as if under a giant blanket, heat from the mantle accumulated. The thick continental plate acted as an insulator, preventing this heat from escaping. Over time, this heat began to literally melt and weaken the crust from within, creating deep cracks that slowly but surely spread across the surface. These rifts were the first ominous omens of the coming breakup. They marked the future boundaries of the Atlantic Ocean and other seas, destined to divide the united world into pieces. At that time, these cracks were still narrow, filled with sedimentary rocks, and only occasionally revealed themselves with bursts of volcanic activity. But they were already harbingers of the coming storm. Our planet has never known true peace. Even in the quietest eras, it was secretly preparing for monumental transformations. The animals that inhabited this new world bore the hallmark of great survival, imprinted in their body structures. Reptiles diversified into numerous groups, destined to become the dominant force of the Mesozoic era. Some remained small and agile, feeding on insects and succulent vegetation. Others grew increasingly larger, their limbs and lungs adapting to efficient and rapid movement on land. The first marine reptiles appeared in the oceans, descendants of land-dwelling ancestors who decided to return to the water to take advantage of the riches of the recovering seas. Their bodies were built for speed and endurance, and their primary prey became abundant fish. Meanwhile, the synapsids, though greatly reduced in size after the catastrophe, continued their quiet evolution alongside the reptiles. Many of them evolved into small nocturnal creatures. Their bodies may have already been covered with the first rudiments of fur, thin insulating layers that helped conserve precious warmth on cold nights. Their teeth became increasingly specialized, their jaws more sophisticated for chewing food, and their metabolism more stable. These seemingly insignificant changes were the first tentative steps toward the traits that would one day define a new class of animals, the mammals. In a world where endurance was valued more than brute strength, these tiny survivors found their advantage in flexibility and efficient use of energy. They lived in the shadow of the giant reptiles, but their time would yet come. One day, they would inherit this planet. Meanwhile, on the surface of Pangea, the atmosphere continued to form. Plants, those tireless workers, absorbed carbon dioxide from the air through photosynthesis, contributing to the overall cooling of the planet and restoring oxygen levels to stable levels. Their powerful roots broke down rock, creating fertile soil and closing the nutrient cycle. Vast forests became living reservoirs of carbon and water, moderating the climate and regulating precipitation. Thus, vegetation itself became a global climate regulator. This delicate connection between life and the environment, severed during the mass extinction, was restored. Every forest, every river valley became a complex living mechanism, maintaining equilibrium. Even when life seemed to have fully stabilized, the planet's memory of the catastrophe it had endured remained forever sealed within its geological layers. The black and red shales of the late Permian period continued to serve as a grim boundary between two eras. They forever preserved the traces of the collapse that changed the face of the Earth. Sharp spikes in carbon isotopes, layers of volcanic ash, and, of course, the fossilized remains of countless extinct species. These stone testimonies preserve the history of a tremendous catastrophe, telling us about the fragile relationship between the planet's chemistry and biology. Each new layer upon them is a story of restoration, showing how new, astonishing life forms arose from the ashes of the old world. The planet itself became a gigantic archive, its stones, its pages, and its surface a chronicle of perpetual movement and renewal. As the new Triassic epoch unfolded, the continents began their slow drift. Cracks in the Earth's crust gradually widened, filling first with water and then with volcanic lava. Giant lakes formed in these depressions, which, expanding, merged with each other, giving rise to new seas. The breakup of Pangea was only just beginning, and it was almost imperceptible on the surface. But within millions of years, these cracks would become full-fledged oceans, splitting the supercontinent into a northern part, Laurasia, and a southern part, Gondwana. This split would once again radically alter the global climate, redistributing heat and moisture flows across the planet. But the trace of this former unity will never completely disappear from the Earth's memory. Mountain ranges born from the collision of continents will long tower above the plains. Their roots will reach deep into the Earth's crust. Over time, erosion will do its work, destroying them too, carrying debris across the continents into the seas. These sediments, in turn, will form new rocks, new layers in the geological record. Thus will the endless cycle of creation and destruction, assembly and disintegration continue. The forces that gave birth to the supercontinent were the same ones that ultimately destroyed it, and sometime in the distant future, its fragments will collide again to give birth to new supercontinents in the endless dance of tectonic plates. The memory of Pangea is more than just a page of history. It is a fundamental law encoded in the very rhythm of the planet's interior. And life followed the same great rhythm, extinction and rebirth. Long eras followed one another, each leaving its indelible mark, influencing the one that would replace it. Organisms that evolved after the Great Extinction carried the genetic and ecological legacy of those who lived before them. Their appearance, their physiology, their behavior, all reflected the brutal pressures of the past: relentless heat, oxygen starvation, and the eternal struggle for survival. Let us fast forward to a world where relentless drought and climatic instability were the norm. The legacy of the giant continent of Pangea was carved not only in the rocks and contours of future continents. No, its imprint lay much deeper, in the very biology of the creatures that desperately tried to survive in this new, harsh world. Every adaptation, every change in body structure or behavior was a direct response to the harsh conditions engendered by the supercontinent's natural environment. Every evolutionary success or tragic failure was inextricably linked to the global systems it set in motion. The oceans that lapped Pangea's vast shores also bore its invisible imprint. Imagine the colossal currents that swirled through the waters of Panthalassa and the Tethys Ocean, their paths dictated by a single gigantic landmass. But then, tectonic forces began to shift, and the continent began to crack at the seams. As the giant plates began to move apart, these global currents were forced to find new routes, creating entirely new pathways for the transfer of heat and nutrients across the planet. The evolution of marine life during this turbulent period mirrored these monumental changes. Species perfectly adapted to the conditions of one ocean basin suddenly found themselves completely isolated, trapped in another. This became a powerful impetus for their further diversification, for the birth of new, unique life forms. The memory of the supercontinent is preserved in the very blood of living creatures, in the common ancestors of species separated today by oceans whose existence in those distant times was unsuspected. Even the very air, the planet's atmosphere, preserved this legacy. Global air currents, generated by Pangea's incredible size and shape, determined Earth's climate for millions of years. They dictated the alternation of devastating monsoons, established cycles of wet and dry seasons, and drew the boundaries of vast, lifeless deserts on the world map. All of this was triggered by that unique configuration of land and sea. And as the continents continued their slow but inexorable journey, these climatic patterns changed, but their ancient foundations never completely disappeared. Amazingly, the climate of our modern planet still retains faint but distinct echoes of those ancient systems. Imagine the merciless sun scorching the red sands of the African deserts. Think of the monsoons that bring life and destruction to Asia, following an ancient seasonal rhythm. Feel the powerful winds that tirelessly cross the Atlantic. In all of this, we see more than just weather phenomena. We see the ghostly legacy of an era when the world was one. Pangea left behind a lasting impact not only on climate and biology, but also on geology itself, on the structure of the Earth's crust. The titanic collisions that created this supercontinent compressed and compacted ancient tectonic plates, hardening their cores. These incredibly stable and durable regions, called cratons, exist to this day, serving as a reliable foundation for modern continents. Deep beneath our planet's shifting surface, in its depths, ancient rocks remain virtually unchanged since the Permian period. These are the physical remains of a superbeing, the skeleton of a dead continent, the most compelling evidence that it once existed and shaped absolutely everything above it. Over time, as the Triassic slowly gave way to the Jurassic, the world would once again change beyond recognition. The dramatic breakup of Pangea would have opened the way to new oceans, created new coastlines on the planet's map, and completely reshaped the flow of air and water. And life, as always, would have continued its great advance, filling every new niche created by these tectonic shifts. Dinosaurs would have grown to incredible sizes, become the undisputed masters of the planet, and eventually evolved into the birds we see today. And the ancestors of mammals, our distant ancestors, would have existed modestly somewhere on the outskirts of this world, in the shadow of giants, quietly perfecting their revolutionary warm-blooded physiology. The world would once again be filled with life and the turbulent flow of evolution. The planet would once again become green and fertile, and the deep wounds inflicted by the greatest extinction in history would gradually heal, hidden under the dense canopy of new forests and vibrant coral reefs. Yet beneath all this splendor, the memory of the supercontinent would have lingered forever. Each breakaway continent would have taken with it a piece of its uniqueness, imprinted both in its rock and in the natural world. Earth's geological cycles would have continued their inexorable course, as they always have. Supercontinents would form and break apart again and again, perhaps 5 or 6 more times over the remaining lifetime of our planet. And each new supercontinent would likely generate its own unique climate and life forms with its own ups and downs. But the harsh lesson of Pangea would forever remain etched in the geological memory of each of them: temporary unity and subsequent separation. Stability followed by chaos. All these processes are inextricably linked. The memory of that ancient supercontinent is more than just a dry geological fact. It's a reflection of how the Earth itself works, driven by its endless internal engine. Our planet is constantly in the process of creation and destruction, and the titanic forces hidden deep beneath its surface and the atmosphere that envelops it slowly but surely shape all life. This planet was once a single whole, but the time came when its fragments began their great drift. The continents we know today were born from these fragments. The mountains that towered to the heavens where they collided would eventually be eroded to dust. The seas that separated them would change their contours, and life would tirelessly adapt to new conditions. However, in the planet's deepest systems, where its global processes originate, the memory of Pangea has endured for eons. It manifests itself in the arrangement of the continents, in the invisible trajectories of ocean currents, in the chemical composition of the atmosphere, and in the quiet but constant movement of the Earth's crust. It is a perpetual reminder that even nature's most grandiose creations are temporary, but their influence can last for eternity. The world born from the ashes of the Permian inherited both the scars and the strength of what had come before. Its landscapes were new, and the life within them was utterly different, but the fundamental structure of planetary cycles remained the same. Continents merged, broke apart, and came back together in titanic embraces. Oceans were born and died. Species evolved, disappeared from the face of the Earth, and reappeared in altered forms. The Earth continued its long, unbroken dance, and within this dance, the memory of every era lived was preserved. The memory of Pangea was just one layer in this great chronicle. It was a record not only of stone and movement, but also of the incredible resilience that defines the very essence of our planet. All of this was subject to the same invisible, profound forces emanating from the very heart of the planet. And each time these titanic processes entered a new phase, the geography, climate, and even the very fabric of life on Earth were transformed beyond recognition. We may think of the continents as separate, independent islands of land, but this is only an illusion. In reality, they are merely fragments of a gigantic mosaic, parts of a single breathing organism, bound together by streams of heat rising from the scorching depths. Gravity and the slow but inexorable movement of the mantle deep beneath our feet generate colossal forces that first stitch the continents together into a single supercontinent and then mercilessly tear it apart. As these titanic plates began their slow dance of convergence, the consequences were truly planetary in scale. Climates across the globe changed dramatically. Gigantic ocean currents shifted their courses, and a time of great trials dawned for all life. Some species evolved, adapting to the new realities, while others vanished forever from the pages of history. But as soon as the continents drifted apart again, thousands of kilometers of new coastlines emerged, entirely new ecosystems were born, and the great history of life began anew. There, at the very end of the Paleozoic era, when the disparate continents destined to become the legendary Pangea began their inexorable drift toward each other, the world stood on the threshold of colossal change. Vegetation was already confidently conquering land. Animals had learned to survive far from the safety of water, and oxygen concentrations in the atmosphere reached incredible levels. The stage was set for the greatest drama in the history of the planet. The northern land masses, which hundreds of millions of years later would become the North America and Eurasia we know today, began to rise from the ocean depths. At the same time, the southern continents, welded together into the single supercontinent Gondwana, slowly crept northward. Between these two giants lay an ancient ocean known to paleontologists as the Reich, and its days were numbered. The subsequent collisions of these tectonic plates literally redrew the map of the world and marked the beginning of an entirely new era in Earth's history. At the sites of these collisions, like scars on the planet's surface, enormous mountain ranges arose, forever changing Earth's geography. But we shouldn't imagine this as an instantaneous catastrophe. Each such collision wasn't the event of a single day or even a single generation. No, this process stretched over millions upon millions of years. After all, time flows differently for the planet itself, and every movement of the Earth's crust is merely a gentle tremor on its age-old surface. The forces at work in that distant era were simultaneously omnipotent and almost imperceptible. Deep beneath the crust, convection currents in the boiling mantle carried heat to the surface like a gigantic conveyor belt. Above, erosion and weathering worked tirelessly, removing tons of rock, transporting sediment into basins where monstrous pressures transformed it into stone. Volcanoes, like fiery beacons, marked the boundaries of impact zones, spewing gases into the atmosphere that altered its composition. Imagine, Every grain of sand, every thin layer of shale or limestone, every imprint of an ancient leaf. All of this was part of a single grandiose process. And when scientists study these geological layers today, they are reading a stone chronicle of our planet. This book is written not in ink, but in the language of minerals and pressure. And within its pages, we find such precise evidence of the movement of the continents that we can trace their paths over millions of years. We know not only their outlines, but also their precise positions in ancient times. This was made possible by minerals that, cooling in magma, aligned themselves precisely with the Earth's magnetic field. These tiny particles, like myriad compass needles frozen in stone, point the way to a vanished world. The very idea that the continents are in perpetual motion revolutionized our understanding of the planet. Geography ceased to be something static and immutable, becoming a dynamic, living process. Mountains no longer seemed like eternal guardians of time. It turned out that, like waves in slow motion, they rise and crumble if given enough time. Ocean basins were born and died, and islands appeared out of nowhere only to sink back into the depths. Even the very air we breathe, the distribution of life across the planet, and the vagaries of climate, all of this turned out to be inextricably linked to this slow, majestic dance of the continents. Pangea was more than just a geological curiosity. It became the central figure in one of Earth's greatest transformations. To better understand this, let's look at our planet from afar, from space. Here they are, scattered across the ocean. Drawn by invisible currents in the mantle, they slowly but inexorably begin their convergence. Tens of millions of years pass, and then they shift another few centimeters. The oceans between them become increasingly narrow, islands crash into one another, and at the sites of these collisions, mountains rise skyward, crumpled into gigantic folds. Gradually, step by step, the Earth is being pulled together into a single landmass. From pole to pole, most of the planet's surface is now covered by a continuous band of rock and soil. And around this supercontinent stretches a single boundless world ocean, carrying its storms and tides across the entire planet. Continents once isolated from one another by thousands of kilometers of water are now united by a common climate system, a single biosphere, and this unity changes absolutely everything, from the direction of the winds to the evolutionary paths of living things. This transformation, impossible to notice in a single human lifetime, has left its scars and imprints on all subsequent stages of Earth's history. Even now, eons after the breakup of Pangea, its traces can be seen in the Appalachians in North America, the Caledonian Mountains in Europe, and dozens of other places. All these mountain ranges, scattered across North Africa and other continents, share a common origin. They were born in the fiery embrace of colliding continents when the great Pangea was forming. The rocks in these ranges tell the same story, a story of colossal pressures and similar minerals. These mountains are silent monuments to an era when the world was one. And fossils found deep within them testify to life that teemed in ancient oceans before the Earth was divided. Every mountain peak and every valley is a fragment of an ancient map, tracing the very moment when our planet took shape. The theory of continental drift is no longer just a theory, but an indisputable fact that still shapes the shape of our planet today. Even now, the continents continue to move, albeit very slowly, just a few centimeters per year. You don't notice it, but it's happening right under your feet. Australia is creeping north, Africa is slowly but surely moving toward Europe, and the Atlantic Ocean is growing wider every year. In millions of years, the Earth will look completely different. New mountains will rise, new seas will appear, and the pieces of this gigantic puzzle will once again fit together in a beautiful pattern, as they always have. When we speak of the birth of Pangea, we are really speaking of only one stage in this endless process, one chapter in this eternal book. It was the moment when the Earth came together from its scattered parts. The mystery of the continents is more than just dry geology. It's a story of movement, of the interconnectedness of all things, and of eternal change. Every grain of sand you touched was once part of something older and grander, carried by winds from mountaintops to river valleys, from one continent to another. The very land beneath our feet traveled across oceans, subjected to unimaginable heat and pressure, compressing and expanding over the course of eternity. The continents were always in flux, and everything else was changing just as imperceptibly. As Pangea took shape, the planet began to feel the effects of this new configuration. The oceans narrowed, the composition of the air changed, and the global climate began to adapt to the existence of this gigantic landmass. It was the beginning of something grand, a global experiment in surviving heat and drought. And somewhere on this vast, unified land, the first creatures began to explore a world that was completely new and unknown to them. They lived under a boundless sky that stretched from horizon to horizon over a continent the size of an entire world. Before the continents merged, the planet looked completely different. Land was scattered across the globe. Individual fragments of it drifted in the slow currents of the mantle, like giant ice flows. Each of these isolated continents had its own unique climate. They harbored their own unique forests and endemic creatures. The seas between them were wide and deep, brimming with ancient life that had never before seen the shores of other continents. If we could look down on the planet from above during that era, it would seem both familiar and completely alien. This mosaic of continents was still in flux, awaiting the moment when gravity and the planet's internal heat would fuse them into a single whole, creating the fabled Pangea. Our story begins approximately 320 million years ago, near the end of the Carboniferous period. In those immemorial times, the planet was a warm, humid, and incredibly green world. Vast tropical forests covered the territories that would become North America and Europe in the distant future. These were endless swamps, overgrown with giant plants and inhabited by amazing amphibians. The air was so saturated with oxygen that insects grew to monstrous sizes. Imagine dragonflies with wingspans like modern hawks soaring above the treetops, and millipedes as long as a grown man crawling along the forest floor, breathing in the thick, humid fog. It was a world ruled by heat and humidity, where every breath was filled with the smell of decay and rapid growth, and every sound echoed across the shallows and dense undergrowth. At that time, Earth didn't yet have a single supercontinent. The continents existed as a disjointed collection of drifting tectonic plates. To the north lay the landmass geologists call Laurasia. It would later form North America, Europe, and part of Asia. To the south lay Gondwana, a vast continent encompassing lands that would eventually split into South America, Africa, Antarctica, Australia, and India. Between them lay the Tethys Ocean, a vast expanse of water that had existed for millions of years. Smaller land masses, like slivers in a stream, drifted between these giants, colliding and merging in a slow but grand dance. These collisions gave birth to the mountain ranges that would eventually become the mountains we know today, laying the foundation for future landscapes. If you could travel back in time and stroll across that ancient land, you would see landscapes that would seem strange, yet recognizable in some details. On some continents, dense coal forests covered tree ferns with fibrous bark and scale-like leaves. On other continents, the vegetation was completely different, with broad, spreading forms. It was a world awaiting a great merger. Let's travel back to a time when the world looked completely different. Imagine endless, flooded plains through which murky, winding rivers slowly flow. They carry with them tons of silt and rotting organic matter, the very material that, millions of years later, would become black gold, the coal seams that fuel our civilization. The air here was thick, humid, and heavy, and sunlight struggled to penetrate the dense green canopy. In this twilight world, giant insects moved leisurely along the tree trunks, and the background sound consisted of the monotonous hum of their wings, the soft splash of water, and the shrill cries of the first, still primitive birds. Ancient amphibians rested, frozen in place, on the banks of overgrown ponds. But a drama of truly tectonic proportions was unfolding on the planet. Two gigantic supercontinents, Laurasia in the north and Gondwana in the south, began their inexorable convergence. And between them, like chips in a vise, were small islands of land, microcontinents. Their fate was sealed. One after another, they collided with the giants, their coastlines crumpled, and the oceans that once separated them collapsed and disappeared forever. These monumental movements were not swift or violent, at least not in our human sense of time. The process stretched over tens of millions of years, driven by the invisible, colossal force of molten rock boiling deep beneath the Earth's crust. On the surface, the effects of this collision manifested themselves gradually and unhurriedly. Mountains rose slowly, centimeter by centimeter. Rivers shifted their courses, and the planet's surface itself subtly shifted its slope. In some regions, volcanoes erupted at plate boundaries. They spewed columns of ash and toxic gases into the sky, which, in turn, affected the composition of the atmosphere and altered the climate across the planet. These changes were almost imperceptible on the scale of a single lifetime, but they were inescapable and long-lasting. The continents themselves at that time were a bizarre mosaic of completely different climatic zones. While the equator was awash in greenery, a completely different world reigned in the far south, right at the pole. Here, colossal ice sheets were being born. The giant Gondwana was encased in an icy shell, and its glaciers, slowly but surely, slid across the lands we know today as South Africa, India, and South America. These icy rivers left deep scars on the planet's surface, scratches and furrows in the rocks that remain to this day, like frozen reminders of the great glaciation. The ice advanced and retreated, obeying great cosmic cycles. Changes in the Earth's orbit, its slight oscillations toward and away from the Sun, forced the glaciers to move hundreds of kilometers back and forth over the course of millennia. Each cycle left its imprint on the layers of sedimentary rock, creating a kind of stone chronicle of those times. But while the southern lands were shrouded in ice, life was in full swing in the equatorial regions. It was the Carboniferous period, a time when warmth and lush vegetation reigned supreme on Earth. Endless rains fed full-flowing rivers that flowed through impenetrable forests of giant horsetails and club mosses. The plants of that era didn't yet resemble modern trees. Rather, they were giant ferns and precursors of conifers that reproduced not by seeds, but by spores. They reached for the dim light, growing incredibly densely, their roots intertwined in a continuous carpet, holding the soil in place and turning everything around into one giant swamp. When these giants died, they collapsed into the quiet, oxygen-free waters of the swamps. There, at the bottom, they didn't have time to completely rot. They were immediately covered by a new layer of fallen leaves and trunks. Layer after layer, millennia after millennia, this plant matter accumulated. Under the colossal pressure and heat of the Earth's interior, it was compressed, lost water, and turned into coal. The same coal that burns in our furnaces today. Think about it. Every spark is a particle of sunlight captured by a plant hundreds of millions of years ago, a relic of a world that existed long before Pangea. Life teemed in the oceans of that era, and it was no less diverse. The warm seas separating the drifting continents were home to astonishing creatures. The famous trilobites, resembling giant woodlice in shells, crawled along the seabed. Ammonites, twisted into intricate spirals, floated in the water column. Ancient fish sported heavy bony armor, and entire cities of coral reefs sprawled in the shallows, built, however, not by modern corals, but by their more primitive ancestors, thriving in the warm, clear waters. The open ocean was teeming with plankton and predators, hunting freely within its vastness, and the seafloor was literally strewn with all manner of mollusks and other burrowing creatures. Ancient sharks and the first ray-finned fish stood at the top of the food chain. The great rhythm of the tides, subject to the pull of the moon, was the same as today. Only everything else was different: the arrangement of the continents, the direction of the ocean currents, and, of course, the species of creatures that inhabited these ancient waters. In this fragmented world, the planet's climate was divided into zones so disparate that they seemed separate. Near the equator, perpetual humidity reigned, giving rise to dense, impenetrable forests. But the farther one moved from the equator to the poles, the lower the temperature and humidity dropped, giving way to entirely different ecosystems. A much harsher, drier climate prevailed in the north and south, and, in some areas, lifeless deserts stretched out. Ice caps at the southern end of Gondwana generated cold air masses that shaped winds and influenced precipitation distribution across the planet. Each continental collision altered air currents and ocean circulation, slowly setting the stage for the monumental changes that would come with the birth of the supercontinent Pangea. It could be said that the planet was preparing itself for its next great transformation. Each continental collision changed not only geography, but also life itself. When two land masses converged, their inhabitants, who had evolved in isolation for millions of years, suddenly found themselves face to face. It was a titanic struggle for survival. This fusion led to veritable explosions of evolution, but also to mass extinctions. Amphibians, once the undisputed masters of land, began to lose this struggle. They were tied to water, their eggs and skin requiring moisture. And then a new, formidable force entered the picture: reptiles. These amazing creatures, covered in tough scales and capable of laying eggs directly on dry land, were ideally adapted to the coming era of drought. They proved to be true conquerors, rapidly spreading across new lands, preparing to become the rightful rulers of the planet in the coming Mesozoic era. Around the same time, in the shadow of these giants, the first ancestors of mammals emerged. These tiny, fussy creatures were part of a lineage destined to survive even the most terrible cataclysms of the future. The collision of continents gave birth to new mountain ranges. As tectonic plates converged, their edges creased like paper and rose skyward, forming majestic mountains. For example, the collision of Gondwana and Laurasia gave rise to the Appalachian Mountains in North America and the Ural Mountains in what is now Russia. In the south, the merging of what would become Africa, South America, and Australia into a single core, Pangea, created two gigantic highlands that determined the climate and weather over vast territories for millions of years. These mountains were not eternal. Slowly but surely, they were eroded by wind and water. Rivers carried away fragments of their rocks, depositing them in lowlands and creating fertile basins where new life arose. Mountains were born and died, but the memory of their grandeur remained forever in the rocks they left behind. In the planet's far north, vast areas of what would become Europe and Asia were covered by shallow, warm seas. These seas literally teemed with life. As the continents slowly drifted toward the equator, their climate became increasingly milder and more hospitable. However, in the southern hemisphere, vast areas of Gondwana remained in the grip of the cold. Due to glaciation and the slow retreat of glaciers, the planet at that time resembled a patchwork quilt of extremes. Here, a humid jungle; there, an icy desert; here, arid plains; there, warm seas. But life found a way to adapt and thrive in every corner of this amazing world. It was an era of great change. As the Carboniferous period gave way to the Permian, the Earth began to change beyond recognition. The era of humid swamp forests was drawing to an end. As the continents clung together, ocean currents were disrupted, and the planet's climate became increasingly dry and hot. The great Carboniferous jungles began to dry out and retreat, giving way to new, more resilient plants. Giant ferns were replaced by conifers and seed ferns. Their main advantage was their hard seeds, which could survive drought where delicate spores perished. Insects also adapted to new, harsher conditions, and reptiles, as we have already mentioned, rapidly expanded their domain. Amphibians, meanwhile, were forced to retreat to the last islands of moisture near rivers and lakes. The entire biosphere was reorganizing itself, adapting to the drier, more continental climate that would soon become the hallmark of Pangea. Deep beneath the surface, in the scorching depths of the mantle, a slow but inexorable work continued. The energy that moved the continents originated in the primordial heat left over from the planet's formation and in the decay of radioactive elements. Vast streams of molten rock, like the Earth's slow breath, rose and fell, dragging tectonic plates with them. These movements influenced not only geography, but life itself. By shifting the positions of the continents, they redistributed solar heat, altered wind directions, and altered rainfall. Over millions of years, they created and destroyed entire worlds, deciding which species would thrive and which would disappear forever. Every tremor of the Earth's crust echoed throughout the world of living things. The world that existed before Pangea wasn't static, but it was balanced in its own way. Each continent represented a unique ecosystem with its own weather, flora, fauna, and evolutionary history. The boundaries between land and sea were constantly shifting, creating an incredible diversity of landscapes. Sea levels rose and fell, flooding some lands and exposing others. Volcanoes spewed lava, creating new islands. Meanwhile, erosion worked tirelessly, wearing down mountains, and rivers carved new channels after each tectonic shift. The planet was always alive, always in motion, but these changes were so slow that they would be impossible to detect in a single human lifetime. Only in the depths of rock, in layers of coal and limestone, in the intricate patterns of fossils, can we read this great story. And so, time passed, and the continents drew ever closer together. Laurasia moved south, Gondwana north. The ocean space separating them compressed like shagreen leather, and the small plates, caught between a rock and a hard place, sank one after another into the mantle, disappearing into the planet's fiery depths. Where the titans collided, a new world was born. Land rose, and new mountain ranges emerged from its depths, leaving gigantic scars on the planet's surface that would one day become the contours of the Great Pangea. Along the edges of these gigantic tectonic plates, entire chains of volcanoes flared like fiery seams, marking the sites of future junctions. Their eruptions threw kilometers-high columns of ash into the sky, and the planet's climate once again prepared for radical change. While the continents inexorably crawled toward each other, the planet's very circulatory system, its global winds and ocean currents, was entering a period of radical change. A multitude of local, disparate weather systems were being replaced by a single, colossal climate machine whose power would extend over the entire future supercontinent. Our planet stood on the threshold of the greatest unification in its history. Even in this pre-Pangean state, Earth presented a truly astonishing spectacle. It was a gigantic, living experiment, frozen in a delicate balance. The world was divided into distinct regions, and in each, life developed according to its own unique rules, but they all remained connected by the oceanic threads, which created invisible yet strong bonds. The seeds of the coming world had already been sown into the soil of time. Those species fortunate enough to survive this era of change would become the heirs of a completely transformed planet. The ancient forests, mighty mountains, and warm seas of the Carboniferous and early Permian had already laid the foundation for everything that was to come. And although the continents were still separated by thousands of kilometers of water, tectonic forces were already inexorably pushing them toward each other. Quietly, silently, but without pause. This great confluence was preordained. It was part of the very mechanics of the Earth. The same indomitable process that had once torn apart ancient supercontinents was now preparing the birth of a new one. All was set for the next grand act in our planet's epic drama. When the drifting land masses finally converged, when the ancient oceans merged into a single mega-ocean, the world would take on a single face. Once again, the slow dance of rock and water led the Earth to its new destiny. A supercontinent was being born, destined to transform all life. A single world, assembled from many fragments, awaited its hour under the dim light of an ancient sun. The continents continued to draw closer. No living creature on the planet could sense it, but the oceans between them were slowly but surely narrowing. Millimeter by millimeter, year after year. Mountains rose from nothingness, valleys deepened, and great rivers changed their courses, carving new paths to the sea. The planet lived its own life, breathing warmth that erupted from the cracks and fissures snaking across the ocean floor. Deep beneath the crust, in the molten mantle, gigantic streams of molten rock flowed, slowly rising and falling in an eternal cycle. These movements were so vast and unhurried that the human eye could never have noticed them, but they were the invisible force, the silent engine that drove everything on the surface. The meeting of continents, the birth of mountains, the endless changes in the face of the earth. All of this was merely a consequence of these deep processes. When Laurasia and Gondwana finally collided, it wasn't a catastrophic impact in our human sense. It was the culmination of a perpetual motion, the result of geological changes occurring on the planet. Imagine a collision stretching over millions of years. It wasn't a crushing blow, but a slow, almost gentle approach of two giants. Two clouds of rock, drifting through space and time, were finally about to collide. However, on the scale of geological time, it was a decisive moment. The Reichum Ocean, which had once separated them, was now closing forever. As its floor was pulled beneath the advancing continents, as if under a giant press, its sediments were folded, heated, and lifted upward, transforming into towering mountain ranges. Rock that had lain dormant in the dark depths for millions of years now began its journey toward the heavens. These mountains, destined one day to crumble to dust, were now the epicenter of tectonic activity, the boundary between two worlds becoming one. Along these boundaries, colossal pressure and heat transformed everything. Imagine pushing together two edges of a huge, heavy carpet. The fabric between them folds into wrinkles. The edges of the colliding continental plates were similarly folded. Layers of sandstone and shale, lying peacefully on the ocean floor, now bent and folded into bizarre new shapes. Minerals crystallized, forming bands and veins that can still be seen today in cross-sections of ancient rocks. From below, granite and basalt rose from the depths, solidifying into solid masses as they cooled. If we could observe this process, we would witness a great transformation. The ocean turned into mountains, and soft sediments into indestructible stone. Simultaneously, volcanic activity along the converging boundaries filled the atmosphere with ash and gases. As oceanic crust sank beneath the continental plates, it melted and molten magma rushed upward. Volcanoes rose in chains, their eruptions covering the young landscapes with lava flows and layers of ash. Each eruption altered the chemical composition of the air. Some gases, like a giant umbrella, reflected the sun's rays, temporarily plunging the planet into a chill. Others, on the contrary, acted like a blanket, trapping heat and releasing carbon dioxide, trapped for millions of years in a rocky prison. The atmospheric balance was disrupted. The planet's climate began to fluctuate, generating cycles of heat and cold that rippled across the entire Earth. And life continued to exist, as always, adapting to the new conditions. The formation of Pangea was not a single giant collision, but rather a series of mergers. Smaller land masses, microcontinents and island arcs, were caught between enormous continental blocks. They were literally crushed and fused into the growing seams of the supercontinent. Each of these fragments carried its own history, the memory of ancient reefs, volcanic chains, and coastal plains. As they merged with the giants, their geological history became part of the grand narrative of Pangea. Today, these fragments can be found all over the world, pieces of once separate landmasses, forever imprinted into the crust of their successor continents. When geologists study these rocks, they see more than just stone. They see frozen movement. Every vein of quartz, every fold, preserves the memory of the enormous pressure and direction of the forces that patiently gripped the continents for millions of years. As a result of these titanic collisions, a mountain belt thousands of kilometers long arose in the territory that would later become eastern North America. The collision with Gondwana raised the ancient Appalachians, majestic peaks that at that time would have rivaled the modern Himalayas in height and power. Far to the north of Europe and western Russia, the Ural Mountains rose according to a similar pattern. In Africa and South America, other mountain ranges rose along fault lines, stitching disparate pieces of land together. These mountains did not arise overnight. They grew slowly, centimeter by centimeter, year after year, as the Earth's crust flexed, fractured, and knit itself together again. And at the same time, erosion, wind and water, worked tirelessly, wearing down peaks as quickly as they rose, maintaining a perpetual balance of creation and destruction. The rivers that flowed down their slopes carried tons of sediment, forming vast new plains, the future home of new life forms. As the continents converged, the world's geography changed beyond recognition. Once distinct coastlines merged, bays became enclosed inland basins, and former islands were swallowed by growing mountain ranges. The remaining ocean, Panthalassa, grew to incredible proportions, covering most of the planet and becoming a single gigantic body of water lapping the shores of the supercontinent. New currents emerged within this mega-ocean. Winds began to distribute heat differently across the planet, and rain began to fall where it had never fallen before. The interior of Pangea became arid regions, cut off from ocean moisture by thousands of kilometers of land and towering mountain barriers. Where humid coastal forests once flourished, sun-scorched savannas and lifeless deserts now stretched. The world lived according to a new climate model, dictated by the slow but inexorable movement of stone. The formation of Pangea affected not only the surface, but also the planet's deep processes. The mantle beneath the crust experienced a redistribution of weight. Where the crust thickened beneath mountain ranges, it pressed downward, redirecting heat flow within the interior. This led to the formation of vast zones of uplift and subsidence. In these lowlands, the crust sank under its own weight, and shallow seas periodically flooded the land, creating vast inland basins teeming with life. When these seas retreated, they left behind thick layers of salt, gypsum, and limestone, silent witnesses to the times when the ocean briefly returned to the very heart of the continent. During this slow collision, earthquakes likely rippled through the growing mountains as the crust released accumulated stress. These tremors shook valleys, split rocks, and reshaped river courses. Each tremor was like the planet's sigh as it adjusted to its new monumental form. It was a quiet but constant hum, a reminder of the colossal forces at work deep within. Meanwhile, hard times had come for the life that had thrived in the damp swamps of the Carboniferous period. The new arid climate and rising mountain barriers mercilessly destroyed the ecosystems that had once stretched across the lowlands. The vast forests that had saturated the atmosphere with oxygen began to shrink. In their place, more resilient plants took root, conifers and cycads capable of surviving in poor, dry soils, amphibians which... Let us transport ourselves to that distant world where the former rulers of rivers and swamps, the giant amphibians, were forced to cede their domain. Their era was drawing to an end, and they retreated to the last islands of coolness and moisture. And at the same time, on the sun-baked plains, a new dynasty was ascending, the reptiles. And all this took place against the backdrop of a truly titanic event, the slow but inexorable birth of the vast supercontinent we know as Pangea. This process was more than just a geological reshuffle. It became the greatest test for all life on the planet. Only those who managed to adapt to the new, increasingly hot and dry climate survived. Those who failed to adapt were doomed to oblivion, their traces forever erased from the pages of history. On the surface of this growing, unified continent, entirely new life forms, adapted to the harsh conditions, were emerging. Imagine these landscapes. In some regions, lifeless deserts stretched for thousands of kilometers, stained deep red by sandstone. And even today, hundreds of millions of years later, we can still discern the faint footprints of the first reptiles and the wings of giant insects on these ancient stones. In other places, turbulent rivers rushed through valleys covered with mighty conifers, rushing toward distant, unknown seas. The air was thick with the scent of resin, mingled with the dry heat of the scorching sun. Enormous dust storms swept across the plains, carrying sand and dust from one gigantic depression to another, slowly, layer by layer, creating what would one day become solid rock. Each layer is a separate chapter in the great chronicle of Pangea, a tale of life and death on its surface. The Earth was literally creating its own history before our eyes. New mountain ranges rose into the sky, shifting the usual wind patterns. Entire animal species embarked on great migrations in search of better conditions. The planet itself, as if writing this saga in stone, underwent subtle changes. As vast land masses shifted closer to the equator, this altered the distribution of weight on the planet. The Earth's balance was disrupted. Imagine a figure skater spinning on ice. By pulling their arms in close to their body, they speed up, and by spreading them out, they slow down. Similarly, our planet, having changed its geometry, slightly slowed its rotation. The days became an imperceptible fraction of a second longer. Of course, this change was so insignificant that no living creature could notice it. But over millions of years, it became another grain in the mosaic of global changes that engulfed the Permian world. The rhythm of day and night remained the same, but the deep, long-term pulse of the planet itself shifted. It was another quiet adjustment in the endless dialogue between the Earth's core and its surface. Volcanic gases erupted from fissures in the newly formed mountain ranges, inevitably affecting the chemical composition of the atmosphere. Sulfur dioxide and carbon dioxide were released into the air in enormous quantities during countless small eruptions. Rain then absorbed these gases, turning them into weak, acidic solutions. These rains, falling on the rocks, slowly eroded them, washing away minerals and carrying them back to the world's oceans. Thus worked the great natural cycle of matter, maintaining the carbon balance and, like a giant thermostat, regulating the temperature of the entire planet. Even amid these colossal, constant changes, the Earth managed to maintain a delicate equilibrium. The coalescence of continents, the birth of mountains, the circulation of gases and minerals, all of this was part of a single, incredibly complex mechanism that sustained the life of the global system. If you and I could find ourselves in the very heart of Pangea, we would be met by a landscape simultaneously familiar and utterly alien. The sky above would be as blue as it is today, and the sun the same golden orb. But the ground beneath our feet would be different, wild, untamed, incredibly ancient. The mountains would be young and jagged, their slopes unsmoothed by time, and fresh faults in the rock would sparkle in the sun with a scattering of minerals. The valleys would still be covered in a layer of volcanic dust, and young, swift rivers would only just be carving their way to the ocean. Try to imagine traveling across this newborn Earth. The world around you would sound different. There would be no birdsong or the buzz of familiar insects. Instead, there would be the low, deep hum of the Earth itself, the hiss of steam from geothermal vents, and the endless whistle of the wind blowing among the bare rocks. This would create a completely unique, primeval atmosphere. Even the air would taste different, with the slight bitterness of volcanic gases and the dryness of eternal dust. In this constantly changing environment, life, as always, sought its own path. Ancient organisms, of course, had no idea of the grand processes that were shaping their world. But their very evolution was a direct reflection of these changes. Creatures living near the equator, in the crucible of eternal heat, developed new adaptations to the dry conditions. Thicker, impenetrable skin, a remarkable ability to retain precious moisture, and, most importantly, eggs with strong shells that could survive and develop far from water. The seas, too, were teeming with life. New species of fish and invertebrates emerged, rushing to occupy the ecological niches left vacant by the extinction of older species. The planet's biology and geology moved in unison, influencing each other like two parts of a single continuous symphony. This slow embrace of stone, the merging of continents, was more than just the meeting of two land masses. It was the merging of entire histories. After all, the geological memory of each continent preserves billions of years of history. Ancient crustal layers left over from even earlier supercontinents, the remains of giant volcanic arcs, fragments of buried oceanic plates, all these elements were part of a single grand narrative. And when the continents collided, these narratives merged into one. Rocks from different eras and origins were compressed with unimaginable force, their minerals intermingled and layers overlapped, creating intricate patterns. Pangea, in a sense, has become a gigantic archive of our planet's past, its crust a repository of all the collisions that have occurred before. And when paleontologists study these rocks today, they read the handwriting of time itself, compressed and rewritten by the heat and pressure of the depths. As the collisions continued for millions of years, the contours of Pangea became increasingly clear. From pole to pole, the Earth became a single continuous surface. The supercontinent stretched in a gigantic arc along the equator, its coasts lapped by the waters of almost all ocean currents. The climate on this new land gradually stabilized and became incredibly diverse. Unbearably hot and dry inland, milder and wetter near the coasts, and cold at the poles. Winds blew incessantly across vast expanses, traveling thousands of kilometers. Rain clouds, borne over the ocean, carried their moisture to the mountains but poured down on the coastal slopes, never reaching the central regions. Deserts expanded, while dense, humid forests stretched along the edges of the continent. It was a world of vast distances, where everything was interconnected, yet each corner of the planet possessed its own unique atmosphere. But even when the continents finally merged into a single whole, Earth knew no peace. The very forces that created Pangea were already preparing its future disintegration. The mantle currents that pushed the plates together would eventually change direction. Deep beneath the crust, cracks would begin to form, stretching the supercontinent in new directions. Magma would rise to the surface again, creating gigantic fissures that would one day become new oceans. This great cycle of creation and destruction would continue forever, like the planet itself, eternally poised between unity and division. However, that moment in history was still a long way off. For now, the world stood united, a single continent surrounded by a single ocean, a world born of fire, pressure, and endless change. The slow embrace of stone had completed its work, though the Earth continued to reshape its creation for millions of years to come. Mountains continued to rise, deserts to advance, and rivers to deepen their channels. But despite all this, life stubbornly continued on its way. It adapted, finding ever new ways to survive on a planet that never, not for a single moment, stopped moving. From the scorching depths of the mantle to the frigid heights of the atmosphere, the Earth was always in motion, always changing, always breathing. The continents collided, the world was transformed, and its new history was only just beginning. By the time the last landmasses finally met, the planet had already been rebuilding itself for tens of millions of years. The slow collisions that began in the Carboniferous period reached their grand finale, and the contours of the new land became clear. Continents that had once drifted freely in warm seas were now tightly locked together, held in place by the unimaginable weight of the converging crust. The birth of Pangea was not a sudden event marked on a calendar. It was a gradual and inexorable process, lasting so long that entire mountain ranges rose from the depths and crumbled to dust before the last oceanic straits between the continents finally closed. The consequences of this prolonged embrace were unprecedented for the planet. From North Pole to South Pole, the continents became one, creating a new ecosystem, unique in its grandeur. Before us, lay a single gigantic continent stretching across the entire surface of the globe. It was the largest supercontinent in Earth's history, occupying almost a third of the planet's entire surface. And around it, as far as the eye could see, stretched the endless ocean of Pangea, its waves washing every coastline in their eternal cycle around the globe. Only to the east, in a gigantic depression formed by twisted fragments of the Earth's crust, did a smaller sea emerge, which scientists call Tethys. It was like a narrow bay, a harbinger of the future oceans that would appear here hundreds of millions of years later. The planet had reached one of the most cohesive states in its history. The world had united into a single stone whole. If you could transport yourself to the surface of Pangea, its sheer scale would stun you to the core. It would be something beyond human comprehension. The horizon would seem endless, and the ground beneath your feet just a tiny part of a vast expanse stretching for thousands of kilometers in all directions. The nearest ocean would likely be a distance you couldn't traverse in a lifetime. Somewhere out there, on the distant coast, it rained, but reaching the arid center of the continent could take months, even years, of travel. Gigantic rivers slowly carried their waters across plains and deserts so vast that crossing them seemed impossible. The climate of this new world was entirely determined by its enormous size. The outskirts were wet and green, but in the interior of the continent, a perpetual drought reigned. Warm winds blew from dawn to dusk, but they carried only a sliver of moisture, insufficient to soften their scorching breath. The formation of Pangea changed everything: the atmosphere, the oceans, and the very life that covered this new, unified landmass. After all, when continents shift, they don't just change the map of the world, they change the world itself. Fast forward to the era when the map itself was rewritten. The movement of continents isn't just a shift in geographic contours. It's a global restructuring that fundamentally alters the climate, the balance of air and water across the entire planet. Imagine the great oceans that once separated the continents beginning to shrink and disappear. Their closure was a catastrophe for the global climate. Ocean currents, those gigantic rivers of heat that had warmed entire hemispheres for centuries, were cut off. The planet's global thermoregulatory system malfunctioned. At the same time, the unification of land into a single supercontinent, Pangea, radically altered airflows. Winds that had previously flowed freely over the oceans now encountered insurmountable land barriers. Clouds began to form in entirely different places. As a result, rainfall ceased to be uniform. The core of Pangea, the vast interior territories where moisture from the ocean simply did not reach, became a realm of stark contrasts. Coastal zones washed by the global ocean of Pangea remained oases of temperate and fertile climate. But the further inland one went, the harsher the world became. At the very center of this colossal continent lay deserts the scale of which is difficult to imagine today. They stretched across what are now Africa, North America, and Asia. And the sands of these ancient deserts have not disappeared. We see them today as majestic red cliffs, a silent reminder of that era of great drought. The mountains, born in the clutches of colliding tectonic plates, were colossal. For example, the Appalachian Mountains in eastern North America were not ancient smooth hills back then, but young, wild ranges. Their sharp peaks had only just pierced the clouds and continued their slow, inexorable rise. The Ural Mountains in northern Eurasia stretched like a giant scar where the two halves of what would become Eurasia met. New mountain ranges arose in the southern hemisphere as Africa slammed into South America and Antarctica. These mountains became the new weather orchestrators. Their slopes now dictated the direction of winds and cloud formations. Air masses encountering these barriers poured all their moisture onto one side, leaving the other in a perpetual rain shadow, dooming it to drought. Mighty rivers born in these peaks carved their way to the ocean, carving deep valleys and canyons into the rock. Millions of years of relentless erosion transformed these mountains into sand and clay, which covered the lowlands, creating fertile plains and basins. These basins became the cradles of new forms of life. The atmosphere at that time was also undergoing colossal changes. The vast Carboniferous forests that once covered much of the land began to retreat and thin as the continents drew closer together and the climate became drier. Oxygen levels, abnormally high during that era, began to fall, approaching levels more familiar to us. The air became thinner and the seasons became much more abrupt and contrasting. Summers turned into relentless heat and winters into bitter cold. Dust storms carried clouds of red dust over the inland plains, while the coasts remained damp. In some regions, monsoon climates set in, alternating seasons of torrential rains and long, grueling droughts. The birth of Pangea didn't simply connect lands, it created a world of harsh climatic contrasts, where conditions in one part of the continent differed dramatically from another. And in this new, harsh world, life continued its eternal struggle, adapting and evolving. The Permian period arrived. The Earth was inhabited by creatures that would seem simultaneously bizarre and somehow familiar to us. Early reptiles and their numerous relatives roamed the parched plains. Some of them evolved into veritable giants, massive and clumsy. Their bodies seemed designed to survive in conditions of water scarcity. Others remained small and agile, darting among the sparse shrubs in search of insects or sheltering shade. It was then that synapsids began their journey, the group from which, millions of years later, mammals, and thus us, would emerge. Even then, they were experimenting with new methods of thermoregulation, learning to survive in a world of extreme temperatures. Even amphibians, which once reigned supreme in the swamps, managed to adapt, finding refuge near rivers and lakes. Forests now grew only where there was water. The ecosystems of the interior were much poorer, consisting of the most resilient and undemanding creatures. Meanwhile, in the ocean that surrounded Pangea on all sides, life was thriving. This global ocean, Panthalassa, was unimaginably vast. Its slow currents, like the planet's circulatory system, carried heat and nutrients across the globe. Along the coasts, in warm, shallow waters, coral reefs thrived, teeming with life. Ammonites and nautiloids swam in the open waters, and schools of fish of all shapes and sizes numbered in the billions. This entire complex system depended on a delicate balance of sunlight, temperature, and currents, now determined by the position of a single supercontinent. The influx of nutrient-rich water from the land caused vibrant blooms of plankton, which fed entire ecosystems. But even here, in these vast waters, the great unification of the land had left its mark. A unified ocean meant fewer barriers between species, allowing them to disperse across the globe. However, this had a downside. Such global interconnectedness made the planet's entire biosphere incredibly vulnerable to any large-scale changes. Geologically, the birth of Pangea was a time of incredible activity. Deep underground, in the mantle, tectonic processes continued. The planet was adapting to the new distribution of mass on its surface. The supercontinent's incredible weight literally pressed down on individual sections of the crust, creating deep depressions that eventually filled with water and sediment. The thickened crust beneath the mountain ranges acted as an insulator, trapping the heat of the interior. This led to metamorphism, a process that transformed old rocks, creating new minerals. A network of faults crisscrossed the continent, and from time to time, the accumulated stress was released in the form of monstrous earthquakes, the waves of which reverberated for thousands of kilometers. Volcanoes, like fiery sentinels, lined the edges of Pangea, spewing columns of ash and toxic gases into the atmosphere. And although from space this world might appear frozen and static, in reality, the Earth was in constant motion, shaking and changing in search of a new equilibrium. The center of Pangea, cut off from the ocean by thousands of kilometers of land, became one of the driest places on the planet in its entire history. Air currents moving inland lost the last of their moisture long before reaching its heart. The result was a vast, dead expanse stretching across what is now Central Asia and North Africa. Plant life here was extremely sparse, only low-growing thorny shrubs and the hardiest conifers, capable of surviving months without a drop of rain. Winds swept unimpeded across the desert plains, raising gigantic dunes of red sand that would eventually harden into sandstone. And yet, even in these hellish conditions, life persisted. Small reptiles and insects adapted to the heat found a home here. The fossil tracks that paleontologists find in these ancient deposits tell us the amazing story of these creatures, fragile evidence of their struggle for survival, preserved for hundreds of millions of years. But as soon as one approached the coast, the world was transformed. The proximity of the ocean created a milder climate with alternating wet and dry seasons. Dense forests of conifers and seed ferns could flourish here. Rivers flowing from the mountains carried fertile silt, enriching the soil and creating conditions for lush vegetation. These coastal zones became true refuges, oases of life, where water and greenery protected countless species from the harsh conditions of the continent's interior. The boundary between land and sea was not constant. It constantly shifted in response to global climate cycles. During periods of cold, the polar ice caps expanded, trapping vast volumes of water. Sea levels fell, revealing new lands for colonization. During warm periods, the ice melted and the sea advanced again, flooding coastal plains and creating new shallow water ecosystems ideal for marine life. Even on a single supercontinent, Earth's climate was never static. The formation of Pangea also had long-term geological consequences. Subduction zones, where oceanic crust plunged beneath continental crust, continued to operate, but they were now concentrated at the supercontinent's margins. Enormous amounts of heat from the Earth's core became trapped beneath the gigantic lid of Pangea. And it was this heat, accumulating over millions of years, that ultimately caused its breakup, triggering rifting, the formation of giant cracks in the Earth's crust. But while this was far off, this heat fueled volcanic activity and the growth of new mountains. The very size of the supercontinent even influenced the circulation of matter in the mantle, slowing the planet's cooling. The Earth came together as a single entity, and this unity was filled with internal tension, balancing on the brink of calm and impending cataclysms. For living creatures of that era, the world was simultaneously united and divided. Theoretically, a reptile emerging in one part of Pangea could have traversed the entire continent in a few generations, as no ocean barriers existed. But in practice, the merciless climate of the inland deserts was a barrier far more formidable than any ocean. Animal populations were isolated from one another, not by water, but by vast deserts and high mountain ranges. And in this isolation, evolution took divergent paths, responding to the challenges of drought and vast distances. Over time, despite the physical unity of the land, completely different ecosystems emerged. Coastal forests bore almost no resemblance to the parched plateaus in the heart of the continent. Life adapted not to the size of the world, but to local conditions. The merging of the continents even affected the chemical composition of the oceans. Rivers, eroding mountains, carried enormous quantities of minerals, phosphorus, iron, and other nutrients into the sea. This triggered a proliferation of marine life, which, in turn, affected oxygen levels in both the water and the atmosphere. But, at times, ocean circulation slowed, leading to catastrophic consequences. Vast zones deprived of oxygen arose in the depths. We can trace these anoxic events today in layers of black shale in the geological record. During such periods, entire sections of the ocean turned into dead, stagnant bodies of water where almost nothing could survive. These fluctuations were merely harbingers, the first peals of thunder before a storm that would soon shake the entire planet to its very foundations. The shadows of things to come, catastrophic climate upheavals and global environmental shifts, were already looming on the horizon, These were the harbingers of change that would ultimately unleash the most devastating extinction event in the history of our planet. But at this moment, during the birth of the Great Pangea, the world was still frozen in a fragile equilibrium. The planet had become whole, stable, teeming with life, and taking on entirely new contours. In many ways, the formation of this single supercontinent marked a turning point in the evolution of the entire Earth system. This event was simultaneously a triumph of order and a prologue to the chaos to come. Imagine, after billions of years of slow, inexorable drift, the disparate continents finally converged, completing a grand geological cycle. However, within this monumental unity, a time bomb was already sown, the seeds of future rift. The forces that had so furiously shifted the tectonic plates showed no sign of settling into eternal slumber. Deep beneath the crust, heat and movement continued to simmer, preparing the ground for a new era of tectonic warfare. But for now, for millions of years, the Earth remained united. In that distant era, the very surface of our planet told a single shared story. From the polar ice caps to the scorching equatorial deserts, every mountain, every valley, was but part of a single, gigantic, unbroken landscape. The creatures that inhabited this land belonged to a world where land boundaries, as we understand them, existed. Only endless, open spaces stretched before them. The ocean, embracing this megacontinent on all sides, filled the air with its boundless power. The winds blew here with such force as if the earth itself were taking a single, long, deep breath. Rivers, with unwavering tenacity, carved their way through the solid surface. The mountains of that time were young and full of primordial energy. Their sharp peaks were eroded by the same eternal cycles of rain and sun that shape today's landscapes. And deep beneath all this splendor, the deep currents of the mantle continued their slow but inexorable dance, sustaining life itself on the planet. The great unification was complete, but the internal movement never ceased. Pangea was not born in a single instant, but as a result of billions of tiny changes accumulating over centuries. The Earth coalesced into a single colossal body, a continent stretching from horizon to horizon, covered by a single sky and washed by a single sea. Every stone, every grain of sand, every wave in the ocean bore the imprint of this grand union. It was a world simultaneously new and unimaginably ancient. For the next 50 million years, life on the planet would be defined by this delicate balance between stability and latent tension. The Earth had finally become one, but the consequences of this unification were only just beginning to make themselves felt, creating unprecedented climates, giving rise to new species, and steering the course of evolution in new directions. As the history of Pangea unfolded beneath the rotating sun, the world, at least for a time, stopped drifting. The continents merged, forming a single, vast landmass that occupied the lion's share of the planet's surface. For the first time in hundreds of millions of years, the Earth stood solid, surrounded by the boundless expanse of a single global ocean. But this unity did not mean peace. The Earth continued its slow, rhythmic breathing, manifested in the movement of air, water, and invisible currents of heat flowing beneath the crust. This supercontinent resembled a gigantic living being, and every part of it, mountains, plains, deserts, and coastlines, was inextricably linked to this deep rhythm of the planet. The atmosphere above Pangea was unlike anything that had ever existed before. The very size of the continent created weather patterns the planet had never known. Air currents that had previously glided freely over the oceans now faced an unprecedented obstacle. They were forced to make a grueling journey thousands of kilometers inland. And along the way, the Earth itself, scorched by the blazing sun, squeezed every last drop of moisture from them. By the time these winds reached the heart of the continent, they transformed into a parching, hot desert breath, sucking water from the soil and plants. The center of Pangea became an extreme. Scorching days gave way to icy nights, and the air was so dry that clouds were rare. It was here that the great deserts of the Permian period spread out, their counterparts today covering much of the modern world. Today, these ancient lands are Central Asia, North Africa, and the southern states of North America. The sand dunes that piled up here millions of years ago left behind the red cliffs we see today. They are silent witnesses to that arid era when perpetual thirst reigned in the very heart of the supercontinent. However, on the coasts, the picture was completely different. The proximity of a gigantic ocean moderated the climate, directing moisture flows inland and triggering powerful seasonal rains. Monsoons, winds generated by the temperature difference between land and sea, dominated the coastline. During the hot months, air rose from the scorching surface of the continent, drawing moist air from the ocean in its place. Torrential rains could last for weeks, saturating rivers to the brim, and coastal forests received abundant moisture for growth. As the seasons changed, the winds reversed, carrying moisture back and returning dry air to the sea. These monsoon cycles became one of the key factors determining Pangea's climate, setting the rhythm of wet and dry seasons, growth and decay across vast areas. In some parts of the world, annual downpours made the soil fertile and vegetation dense. However, in other regions, they brought only temporary relief, after which the drought returned with renewed vigor. The planet's climate is a complex and often unpredictable system. The interaction of a single supercontinent and a single superocean, Pangea, generated air and water circulation on a scale never before seen. Heat accumulated on the land, while Pangea absorbed and redistributed it through slow, deep currents. The contrast between land and sea temperatures generated winds that shaped global weather. Near the equator, warm, moist air surged upward, fueling powerful storm systems. And at higher latitudes, cool, dry air sank, creating arid belts that extended across much of Pangea. The balance of these forces was constantly shifting. Over time, Earth experienced climate cycles lasting thousands, even millions of years. During some periods, the planet warmed, polar glaciers melted, and sea levels rose. During others, the poles cooled again, and ice sheets spread along the southern edges of Gondwana. These fluctuations were influenced by changes in the planet's orbit, its axial tilt, and even the composition of the atmosphere. Volcanic eruptions along the supercontinent's seams released gases into the atmosphere, including carbon dioxide, which, like a blanket, trapped heat and influenced global temperatures. Ash from these eruptions could temporarily cool the planet by blocking sunlight, while the long-term effect of greenhouse gases most often led to global warming. The climate of the Permian period was a complex mechanism that constantly changed, reflecting Earth's perpetual adaptation to internal and external forces. The air that filled the skies above Pangea was thinner and drier than what we're used to. During the preceding Carboniferous period, which was incredibly rich in vegetation, giant swamp forests flourished. At that time, plants actively absorbed carbon dioxide and produced oxygen in colossal quantities. However, over time, these wet forests began to disappear, giving way to drier ecosystems. This caused the chemical balance of the atmosphere to shift dramatically. The oxygen content in the atmosphere plummeted to approximately 20%. This value is very close to what we breathe today, but it was a pale shadow of the age of gigantism. After all, at one point in the past, oxygen concentrations reached an incredible 35%, and it was this thick, life-rich air that allowed monstrous insects the size of birds to thrive. The decrease in oxygen affected the size and metabolism of many species. Insects became smaller and forest fires became less frequent because the air could no longer so easily support combustion. The atmosphere found a new equilibrium, shaped by the vast expanses of land and the changing face of life. The continent's surface itself directly influenced the atmosphere above it. When the sun rose over the inland deserts of Pangea, the rocks and soil rapidly absorbed heat, creating a unique microclimate. The air began to warm, and powerful updrafts formed convection currents in the atmosphere. These movements, in turn, drew cooler air from the coast, further intensifying the monsoon cycles that determined the seasons. At night, the land cooled just as rapidly, and temperatures could drop by tens of degrees. This daily cycle of heating and cooling in the inland regions was far more extreme than when the continents were separated by oceans. The supercontinent greatly intensified the contrasts between day and night, between moisture and drought, heat and cold. It was a world of constant and dramatic fluctuations. Even with its long-term stability, life continued to thrive. Mighty rivers meandered through the coastal lowlands, carving wide valleys and carrying sediment from the mountains to the sea. Each flood season brought new layers of silt, creating fertile plains where coniferous forests and seed ferns flourished. These plants, with their deep roots and leaves capable of retaining moisture, were ideally adapted to the new climate. They could survive both dry periods and devastating floods. Spreading across all continents where conditions permitted, they stabilized the soil and created a favorable environment for animal life, laying the foundation for Pangea's terrestrial ecosystems. The air here was filled with the scent of resin and dry earth, as well as the buzzing of insects and the rustling of small reptiles scurrying through the undergrowth. Inland, where rain was rare, vegetation was much more sparse. The landscape here consisted of rocky plateaus and endless dunes of red sand. Only occasional oases supported life, clustering around them pockets of hardy plants, insects, and seasoned reptiles. These isolated ecosystems were like small fortresses of life in the midst of a lifeless desert. Imagine these oases, green islands lost in a vast ocean of scorching dust. Here, life clung to every chance, and survival depended entirely on the mercy of nature, on the rare, life-giving showers brought by distant thunderstorms. The local inhabitants were true masters of survival, forged in the crucible of this harsh world. The first reptiles achieved a true evolutionary breakthrough. Their skin became covered in thick scales, a natural armor that reliably protected them from the scorching sun and minimized the loss of precious moisture. An equally ingenious invention was the hard-shelled egg, capable of developing even in the dry, merciless air. They found refuge from the daytime heat and predators underground, digging deep burrows that became a safe haven for themselves and their future offspring. Only at dusk, when the deadly heat subsided, did these creatures emerge from their shelters in the shadows of the rocks to search for meager food. Even today, millions of years later, the ancient desert sandstones preserve a silent record of that era. Fossilized footprints, forever imprinted in the stone, tell us stories of the wanderings of these ancient creatures. These tiny winding chains of imprints on the rock surface are like autographs left by time itself. Even the gigantic ocean of Panthalassa, which occupied most of the planet, was not uniform. Its character and behavior were entirely dependent on the configuration of the surrounding lands. The enormous currents, slowly and inexorably creeping across its surface, were driven by the eternal rotation of the Earth and the uneven distribution of solar heat. But the Tethys Sea, wedged between the eastern extremities of Pangea, became a true lost paradise, a cradle of marine life. This warm, shallow expanse of water was dotted with intricate reefs built not by modern corals, but by ancient sponges, algae, and the very first primitive forms of coral. Schools of fish darted carefree in its azure waters, and ammonites swirled with their spiral shells. And just below the surface, in sunlit layers, drifted countless myriads of plankton, the foundation of the entire food chain. These ecosystems were incredibly rich and diverse, a true incubator, giving birth to countless new species that would only conquer the world's oceans when the continents began to move again. However, the depths of the great Panthalassa Ocean painted a completely different, bleak picture. They were far less welcoming. The unimaginable size of this aquatic giant created a problem. Water circulation in its bottom layers was extremely difficult. This led to the formation of vast, dead zones with catastrophically low oxygen levels. We find evidence of this in the geological deposits of that time. Dark, organic-rich strata formed when the remains of dead organisms sank to the bottom and rotted in stagnant, oxygen-deprived water. It seemed life itself was suffocating here. The majority of marine life huddled near the coasts and in shallow waters, where sunlight and nutrients were abundant. But even in the bottomless darkness of the ocean depths, there were those who managed to adapt to the eternal gloom and oxygen deficiency. These amazing, unique creatures also left their mark on the planet's rock record. The ancient ocean, like the land, was a world of striking contrasts. In some places, it was teeming with life, while in others, it was cold and empty. The atmosphere that enveloped all this primeval splendor was also heterogeneous. Columns of dust, raised by winds from the central deserts, soared high into the sky and spread across the continent, even reaching distant oceans. Powerful volcanic eruptions released millions of tons of aerosol particles into the air, which, like a giant filter, altered the way sunlight was scattered. These particles directly influenced the weather and global climate, sometimes causing temporary cooling and sometimes, conversely, enhancing the greenhouse effect. They also served as condensation nuclei, around which clouds formed and rain fell. Over geological timescales, these effects compensated for each other, but in the short term, they introduced an element of chaos and unpredictability into the planet's weather. One could say the supercontinent literally breathed this endless cycle of dust and rain. Its climate was a direct reflection of the complex interactions between rock, air, and life. This connection between the land and the atmosphere was inextricable and constant. As plants spread across the planet, they altered the gas composition of the air, greedily absorbing carbon dioxide and releasing life-giving oxygen. When the climate became hotter and drier and vegetation retreated, the reverse process occurred. This global feedback loop acted like a giant thermostat, helping to regulate the Earth's temperature and keep it within limits suitable for life. The birth of Pangea only intensified this interaction, as a huge landmass was now concentrated in one place. Weathering processes that eroded mountain ranges caused rocks to react chemically with the atmosphere and absorb carbon dioxide, which in the long term led to a cooling of the climate. But then came the turn of volcanoes. Their increased activity released new batches of greenhouse gases into the air, which neutralized the cooling effect and returned heat back to the system. As a result, the planet's climate became incredibly dynamic. This slow, majestic oscillation between warm and cold periods, this delicate balance, sustained the flame of life on the planet. As millions of years passed, Pangea's ecosystems grew increasingly complex and resilient. Dense forests stretched along river valleys and coastal plains, and vast deserts were stabilized by giant wind-sculpted dunes. Reptiles rapidly evolved, giving rise to ever-new forms perfectly adapted to diverse climatic niches. Insects mastered the art of pollinating the first seed plants, laying the foundation for ecological relationships that would endure for hundreds of millions of years. Even in the driest and seemingly lifeless corners of the continent, a subtle hum of life hung in the air. Everything obeyed the single rhythm of the planet, the rhythm of rain, wind, creation, and destruction. This supercontinent had its own unique weather, its own distinct seasons, and its own distinct, measured, and prolonged breath felt across entire geological epochs. The Earth's magnetic field, like lava frozen in stone, also bore the imprint of this era of unity. As streams of molten magma erupted onto the surface and cooled, tiny particles of magnetic minerals within them aligned precisely with the direction of the planet's magnetic field lines. These minerals, like millions of microscopic compasses forever frozen in stone, preserved invaluable information about the precise location of the continents at that moment. By studying these ancient magnetic patterns today, scientists can, like detectives, track the drift of tectonic plates and reconstruct with astonishing accuracy not only the outline of Pangea itself, but also the paths of its travels across the planet. The supercontinent's breath was felt everywhere, not only in the atmosphere, but also deep within, in magnetic fields, in geochemical cycles, in all layers of the Earth. Pangea's climate systems exerted a colossal, albeit invisible, influence on the biosphere. Sharply defined, extreme seasons forced animals to adapt and migrate. They developed complex survival strategies in conditions of resource scarcity. Some learned to hibernate, others hid in deep burrows, and still others undertook epic journeys over vast distances. Plants developed seeds capable of remaining dormant for decades, patiently awaiting the return of the rains. Evolution became a tense dialogue between living organisms and climate, with each side shaping and modifying the other over eternity. The creatures of that Permian era weren't yet the giant dinosaurs that would one day become the sole rulers of the Earth, but their distant ancestors had already undergone the harsh school of survival in this volatile world. The supercontinent became a true testing ground for them, where the reward for resilience was life, and the key to survival was narrow specialization. The deserts that covered much of Pangea's interior were truly gigantic, but by no means lifeless. Among the sand dunes, lowlands could be found that, after rare but fierce storms, would fill with water, turning into temporary lakes. Around these ephemeral oases, algae would bloom, clouds of insects would swarm, and herds of starving animals would flock to the water. When the water evaporated under the scorching sun, salt crystals remained on the surface, forming a dazzling white crust that shimmered in the sunlight. The next rainstorm would trigger a new cycle, and the sediments of these ephemeral lakes preserved priceless fossils, telling us about those who came here to drink. Paw prints, bones, and tracks left in the drying mud provide irrefutable proof that life never gave up, even in the harshest conditions. Yes, despite its vast and arid expanse, the supercontinent supported a complex web of ecosystems linked by flows of water and air. Pangea's breath permeated even its rocks. As mountains eroded, their sedimentary rocks, containing certain minerals, reacted with the atmosphere, binding carbon and forming new chemical compounds. These slow, invisible processes helped regulate the chemical composition of the entire planet. The weathering of silicate rocks removed carbon dioxide from the atmosphere, and volcanic activity returned it. Thus, despite the harshest conditions, life continued its great uninterrupted cycle. The balance between these two powerful forces kept the climate relatively stable for millions of years. The Earth was a gigantic self-regulating system, using its geological and biological mechanisms to maintain a delicate equilibrium. The formation of Pangea did not upset this balance, rather it became an integral part of it. It was merely the latest manifestation of the profound feedback loop that had governed our planet since its inception. To live on Pangea was to experience the world as simultaneously infinitely vast and astonishingly cramped. The horizon seemed never-ending. Every storm, every gust of wind, every movement of air was part of a single global system. The very monsoon that brought life-giving moisture to coastal forests could dry up completely within weeks, giving way to dry winds blowing from the center of the continent. Dust raised in the heart of the deserts drifted over the oceans, fertilizing plankton with vital micronutrients. Everything was linked by a slow, majestic circulation, an eternal exchange between sea, land, and sky. The Earth breathed, and this breath embraced the entire planet like a single living organism. Although the continents on the surface stood frozen in a single monolith, movement beneath them never ceased. The mantle beneath the crust continued its slow flow, and heat currents from the Earth's interior rose and fell like the beating of a giant hidden heart. The crust buckled under its own weight, creating new faults and cracks. For millions of years, heat accumulated within, repeatedly increasing pressure and laying the foundation for the next great rift. But at this point in its history, the planet seemed frozen. The supercontinent stood immovable. The air above it pulsed, creating gigantic vortices that carried heat, dust, and life across the globe. The Earth breathed deeply and steadily, balancing between creation and hidden tension, as if crouched in anticipation of what was to come next. The land was united, the air was dry, and the seas were bottomless and boundless. And in this primordial silence, life continued its journey.